In this, we will review derivatives of all major functions using different type of techniques. For example, we're going to talk about power rule, product rule, quotient rule, chain rule, and at the end, the implicit differentiation. And that's going to cover like all the topics that we learn in Calc 1. And also, we're going to discuss several different functions, like for example, we can do polynomials, rational functions, exponential functions, logarithmic functions, trigonometric functions, and even inverse trigonometric functions. So you're gonna see all of them here. So as problems, we're gonna find derivatives of functions like these. For example, what is the derivative of a rational functions? So for example, x to the fifth power cube root. So that's a rational function, or what we normally, not the rational functions, radical functions. So we're gonna find derivatives of function like that, and then we also find derivatives of, for example, let's say um, exponential function of this type. So it's like a special exponential function. It's a function to function, and we need what we call logarithmic differentiation for that. And also we're gonna do like a product rules like this, like for example, let's say x cube e to the 2x, something like that. So that's a product. So we have is a product rule for that. And then we also gonna find a derivative like a complicated function like this. So let's say for example, cosine cube to the let's say tan inverse e to the x squared, something like that. Even though it's little looks complicated, um, it's easy to find the derivative using what we call the chain rule. And we also do like for example the quotient rule. Like for example, we're going to find the derivative of a function like this. So so this is what we call a rational function. So we can say 5x minus 2, something like that. That's a rational function because you divide two polynomials, you get a rational function. You can find the derivative of that. So that's for the quotient rule. And then also some exponential function like this. Let's say for example 3 to the 4x. What is the derivative of this one? And also the exponential function using e. So for example, what is the derivative of e to the 2x plus 1? And also there are results for like a log function. Like for example, what is the natural log derivative of natural log ln x to the fourth, let's say minus 3x, something like that. And also we can find derivative of certain trigonometric functions. For example, how about tan inverse, let's say x to the fourth power, or maybe plus 1, like that. So what's the derivative of this one? And also like some a composite function. Let's say x to the sixth power plus x to the 3 plus 1 whole thing, maybe a fourth power. So what is the derivative of this one? Also at the end, we're going to find the derivative of um, implicit function. For example, let's say you have something like this, x cube plus xy equal, let's say natural log x squared plus y squared, something like that. And you can see that this is an implicit function because you can solve for y, but we can still find the derivative of this function. These are special functions, these are like implicit functions. So we can do like all kind of functions like this involving trigonometric functions, so exponential, products, quotients, radical functions, everything. Okay, so we can go one by one. So we can start with the most basic rule, what we call the constant function. So let's talk about that first. So so let's start with the constant function. Constant function. So what's a constant function? Constant function means you have a function y equal a constant. So if you look at the graph of this function, it looks like that. So let's assume the constant is positive. So you're going to see a constant like that. So and then we know that there's a value c. We know that the constant so that's a constant function. We know that the derivative is the slope of the graph. So what's the slope? So if it's a constant function, slope is simply becomes 0. So the slope is 0. So that means the derivative has to be 0 for that function. So that's the first property. So that means we know that, so I'm going to write the result here. So if we have a constant function, so let's say c as a constant, so the derivative is 0. So that's the first result, um, because you can see the slope is 0. Okay, so let's look at some examples. Um, so for example, what is the derivative of the constant function 3? So which is 0 according to this result. Okay. So it can be anything. So so we can have a few more. So what is the derivative of 100? Still 0, okay, because it's a constant. And what's the derivative of this function? Let's say pi to the e. So pi is a good number, this is a good irrational number, e is a good irrational number, and if you raise, it's still a constant, so it doesn't really matter. So it's still 0. Okay, so those are like some values can be positive, negative, even fractions, like for example d over dx, negative 1/2, still 0 because it's just a constant. Good. How about this one? D over dx. Let's say tan inverse pi over 4. Something like that. Don't get confused. It doesn't matter what you have, it's just a number. So that means it has to be 0. Okay? Good. So that's the first one, the constant function. So let's go to the next important one, what we call the power functions. So the next one is the power functions. Power functions. So what's the power functions? Like when you have a function like this, y equal x to the n, that's what we call a power function. So what is the so n is a constant, okay, that's the only condition. N is a constant. N is a constant. So the power function have several different type of graphs. um, so so we can have so I'm gonna consider several cases. So let's start with the most common ones. So what's the most common one? One is the y equal x. So that's the most common one. So that's a y equal x function. It is y equal x. So this is x to the 1. That's the first one. And what's the next one? Y equal x squared. So let's graph the second one. So let's graph most common ones because these are useful for your calculus classes. So this is y equal x squared, what we call the parabola. So the graph, so this is y equal x squared. So that's called parabola. So look at the shape of the graph. Okay, those are not straight lines, and it is symmetric. And what other power functions we know? Y equal x cube. So let's graph y equal x cube. So so it is like this. It's like that. So that's the y equal x cube graph. Y equal x cube. So these are all power functions. What else we have? So what if n equal -1? So you're gonna get a graph like this. So when n equal -1, it is 1 over x. So the graph looks like you can see when the numbers getting smaller, 1 over x getting larger, and when the numbers getting larger, it gets smaller. So that's the graph of 1 over x. And when you have negative, it's negative. So it's just a reflection or across the origin. So this is y equal 1 over x. And then we have 1 over x squared. So what is the graph of 1 over x squared? So you can see it is very similar. Only thing is now both sides are positive because x squared, so it's gonna get like that and gets like that. Okay, so so this is y equal 1 over x squared. So these are all power functions. And then we also have square root function. That's also power function. If you say n equal 1/2, you're gonna get this one. So so this is the square root function. So it goes like that. It's increasing. Okay, so this one is y equal square root x, and then we have one another power function. So this is the y equal x to the cube root. So y equal x to the cube root, or 1/3 power. So you can see uh, square root only defined for non-negative values, so it can be 0 or positive, but the cube is defined for negative values as well, so that means you're gonna get the other side as well in this case. So so it's gonna go like that and then go like this. So that is the um, cube root function. Okay, it's not flat, still decreasing, so it's gonna go down like that. Okay, and it's symmetric about the origin. Good. So that's the cube root function. So those are the several common functions that you need to know, and including and then the constant function is you can write that as a power function, because x is, when you have x, you're gonna see some changes. So the constant function is not a power function. But so these are the common power functions you need to remember for calculus classes. Okay, and then I'm going to draw like one last one, and you can see if you want to graph, like say y equal x to the 4th power. If you want to graph y equal x to the 4th power, so what's going to happen? You can see it is very similar to y equal x squared. It's only more steeper. So so what's going to happen is, so it's going to go grow like that, and it's very close to 0, and then grow like that. So it's like a this looks like y equal x x squared, but it's more close to 0. When close to 0, the values are smaller. Okay, so that's the only difference. And then one of the interesting things is all these graphs pass through the point 1 1, because you can see when you plug in 1, it's all 1. So all of these graphs pass through the point 1 1. So this is y equal x to the 4th power, and then all these graphs pass through the point 1 1. Okay, so I will just only put this in one of them, but you know that all this passes through the point 1 1. Okay, the reason is when you plug in 1, it is 1 for all of them. Okay, good. That fact is important sometimes when you try to solve certain problems. Okay, so those are the power functions, and let's see how it looks like, when you try to use the derivative. So we know that we have the power rule. So let's talk about the power rule. So what's the power rule? What we call power rule. So the power rule is if you take the derivative of a power function x to the nth, result is n x n minus 1. Okay, that's what we call the power rule. Only condition is n has to be a constant. That's it. Okay, so all the power functions follow this general rule. So the only condition is n is a constant. N is a constant. And also you need to think about the domain. For example, if n is 1/2, you know that it's going to be negative, because otherwise it's going to be complex. So we need to think about that as well. But otherwise, as a general function, this is what we call the power rule. The power rule. So for any n, okay, for any n. So let's try to solve some problems from that. So let's start with something easy. So let's solve some problems. So let's say what is the derivative of x squared? X squared. And we don't need a parenthesis around it because there's only one function and it's clear what it is. Okay, so don't use unnecessary parenthesis around because it can complicate. Okay, so if you don't need, don't write it. Okay, so no, we don't write parenthesis here. So it's just d over dx squared, because you don't need that for the function. Okay, but if you have a product, you need. So now we can use the power rule. According to power rule, in here n equal 2. That's the n. So if n equal 2, what you get is 2x 2 minus 1. That's what the power rule says. So that means if you simplify it is 2x to the 1. We do not write 1 because that's obvious one. So we just write 2x as the solution, because we write the most general, most simplified form. So that's the most simplified form. Okay, so just try to get used to it. That's how you write good mathematics. Okay, and then let's go to another one, and it doesn't really matter what the variable is, so you can say dt, but then make sure that the function is also in t, so t cube. Again, we don't write the parentheses because it's obvious what it is. Okay, so let's get used to write things properly. Okay, it's very important to make things simple and to make things good, especially when you write something, okay, or report or something, you need those things, right? Okay, so again, here n equal 3, so that means it is 3t 3 minus 1, so it is 3t squared, so we leave it like that. Okay, so that's the solution, that's the derivative. Next one, how about this function d over dx square root x? So when you see something like that, if you do not see what is the power, let's rewrite it. So I'm going to write this one d over dx. Square root means x to the 1/2 power. Okay, now we know what is n. So the n is 1/2. If it is not clear, we can do that. So now we take the derivative. So if you take the derivative, it is 1/2 x 1/2 minus 1. So that means 1/2 x. If you subtract 1 from 1/2, it is negative 1/2. So it's clear. You are in Calc 2. Okay, now we normally do not leave negative index in final answers. So if you get a negative index, what you want to do? You want to bring it to the denominator. We know that when you switch from either numerator to denominator or denominator to numerator, it's gonna change the sign of the index. Okay, so it's gonna change the sign of the index. That's exactly what happens. So that means it's gonna be 1/2 1 over x to the positive 1/2. Okay, change the sign of the index. That's what happened. Change the sign of the index. Now we know that x 1/2 means square root. So the best way to write this one is 1 over 2 square root x by combining. So we write the answer like that. Okay, because this is much clear. And you can skip many steps if you can do some steps, but I'm writing all the steps, especially at the beginning. Okay, so let's try to do some special cases. How about our obvious one? If you have d over dx x. So if you have d over dx x, what is the power here? We don't see the power. So x means what? X means x to the 1. Okay, so you can rewrite always. Now let's use the power rule. So n is 1. So that means your solution is 1 x 1 minus 1. So what is 1 minus 1? 0. So it is x to the 0. So let's assume that x not equal to 0, because if x equals 0, this does not gonna work, because you get 0 0, that's an indeterminate form. So so let's say x not equal to 0, so then we know that x to the 0 is 1. So that means this quantity is simply 1, assuming x not equal to 0. So that means your final answer is simply 1 times 1 is 1. So that if you take the derivative of x, you get 1. This is a interesting result, and we can use this a lot. Okay, a lot. So let's talk about a few more cases as well, like some complicated ones. So how about this one? So let's say we have d over dx 1 over x. So if you have 1 over x, what is this? It is simply, again, d over dx 1 of x means x to the negative 1. It may be easy to do it first before we do that, okay? And then now we know what is the n. So n is negative 1, okay? So if n is negative 1, it is negative 1 x negative 1 minus 1. So that means we have negative, we don't need to write negative 1 anymore, because negative means negative 1 means negative. So negative x, and you can see negative 1, negative 2. Again, the same law. We don't leave the negative index in the denominator anywhere. Okay, we can change it to the other side. So that means you're going to bring it down. So you can write this one as negative 1 over x squared. Good. Okay. And then also, like, I'm going to write this small note. Where to write the negative sign? Don't try to write this answer like this. Negative 1 over x squared. I have seen like people writing like that. that's not really simplified well, because it's still asking you to divide -1 by x squared. So that is not the most simplified form, okay, because you still have to do one more step, because you have to divide -1 by x squared. So that means don't try to write your solution like that, because that's not most simplified form. So most simplified form is you write the negative term in front, okay, it is -1 x squared, okay, that's what it means. So just try to write the solution in a proper way, okay. So that's what we call we learn something. Okay, good. So the solution, so if you have a -1, make sure that you write that in front, okay, good. So not like this, okay, so this is not the most simplified form. Good. So let's do more. How about this one? Let's say d over dt 1 over t cube, okay. So the same argument. So what we can do first, we're gonna bring t the power to the top, so we can write it like that as a power function. Now we know what's going to happen. So -3t, you subtract 1, -4. Now you can do it, okay. You can skip that step, so you can just write like that. Okay, again, negative powers, that means -3 over t to the 4th. So that's how you write the final answer, okay, -3 over t to the 4th power. Okay, I hope you learned something now. Good. So let's try to maybe few more examples, just little complicated ones. So d over dx, let's say we have, how about you're gonna see something like this. Let's say t to the 4th power cube root, just some numbers, just put some numbers there. Okay, so this is a radical function. So when you have a radical function, the first thing that you do is you write this as a power function. Again, actually there's a typo here, because that's x, this will be t, so this will be t. Otherwise you can take the derivative there, because it's two different variables. So we now talk about partial derivatives. That's like calc 3 topic. Okay, so let's try this as a power function first, as we did. What is the cube root means? 1/3 power. So that means this is t to the 4th power 1/3. So that means it is d over dt, t to the what? When you have power of a power, what's going to happen? There are two powers. You have one power and you have another power. What normally happen is you multiply the two. Okay, so you multiply the two. That means you can write this one as 4/3. So that's the power we need. Okay, you have to simplify up to that. Okay, now we can use the power rule. So according to the power rule, the power comes out, and then t 4/3 minus 1. So this is very easy to simplify. You can see this is 4/3 t to the 4/3 minus 1 means you subtract 1, you get 1/3. 1/3 means the cube root, so that means the final answer is 4/3 t to the cube root. So that is a good way to write the final solution. Okay, I sometimes draw two lines to make sure that that's where you stop. Okay, that's the final answer. Okay, so that's the final answer for that problem. So let's do another one. So how about this? So let's say d over dx 1 over x, let's say 3 to the square root. How about that? So again, when you have radical functions, you need to write this as a power function first. So let's write that. So that means it is 1 over x to the 3/2. We're going to bring it up. So that means x to the -3/2. Now we can use the power rule. Okay, so that's where we can use the power rule. So let's do that. So that means -3/2 x to the, you subtract 1 more. So what do you get? When you have -3/2 minus 1, take the common denominator. You can see to get the common denominator, you need to multiply by 2 top and bottom. So that means this simply becomes -3/2 x to the -5/2. Okay, that's clear now. Okay, now what we're going to do is a negative power, bring it down. So when you bring it down, so it is -3/2 still there. You can write this one as 1 over x to the 5/2. 5/2 means what? this is a product. You can write this one as 5 times 1/2. 1/2 in the square root. So that means you can write the final answer as negative 3/2. You can say 1 over x to the 5th power square root. You can write it like that. Okay. So that's one way to write the final answer. Or both are okay. And then you can also write 3 negative 3 divided by 2, and then this one we have. So you can write any of them. Okay, both are okay. So any version works. You can use as a final answer. Okay, so both okay. So I'm going to give you one for you to try. So you can try this one. So this is an exercise for you. So I'm going to say exercise. So what is the derivative of 1 over x to the 4th power 7th root? Okay, so what's the answer? And you can see the answer in the description. Okay, good. So that's about power rules. So let's go to so what is the derivative of power function? Okay, so you can see what the best thing that you can do is just redo it, and until you are comfortable with that. So let's next go to the constant multiple results. So there's nothing much here. So what it says, the constant multiple. Okay, constant multiple. So what's the constant multiple result? It says that if you have a constant times a function, I'm going to put a parenthesis around here, bracket around here, because there are two functions, so you need a bracket. Okay, what it says, you can just pull the constant out, okay, and then just take the derivative of the function. And here we don't need a bracket because it's clear now. Okay, that's what it says. If you have a constant, pull it out. Okay, that's what we call the constant multiple rule. Simple. Just pull the constant out. Good. So let's do few, because we don't need many now. So how about this one? Let's say what is the derivative of d over dx? 5 times x to the 4th power. Here, okay, now there's a question. Do we need a bracket or not? Parenthesis or not? You can see there are two functions here. One is 5, the other one is x to the 4th power. If you do not write a bracket here or parenthesis here, it means that take the derivative of 5 and then multiply by x to the 4th. So that is completely different from this. So that means in this case you need a parenthesis. Otherwise it means something else. Okay, so be careful with that. So you need a if you have more than one term, you need a parenthesis around it. Especially when you have sum, you need a parenthesis. Otherwise you only take the derivative of the first term. Okay, so that's different. When you write mathematics, you need to write mathematics correctly, because otherwise it has a complete different meaning. Okay, we need to avoid them. Okay, so now so we use the constant multiple rule. That's a constant, so take it out and just take the derivative of the second term. So what do you do? Take the derivative of x to the 4th. That's what this says. Okay, so that means 5. When you take the derivative, it is 4x to the, so subtract 1, 3. Now what we can do, we're going to combine these two. So when you combine these two, 5 times 4 is 20, x to the 3rd power. Okay, that's the final answer. Okay, I also need one more word here. You can see in the previous step, I write 5.4. So there are, this is like actually also important what I'm writing here. So there are two things. You can write 5.4 versus you can write 5.4. See where I put the dot. In the second one, I put the dot in the middle. In the first one, I put dot in the lower level. Those two are two different things. In the first one, it means 5.4. Okay, 5.4. In the second one, it means 5 times 4. Okay, they are not equal. So be careful when you write the dot sign. So that means it's not equal to 5.4, because here we put the dot in the middle. That means the multiplication. Okay, that means the multiplication. So be careful with those. Okay, because sometimes we even ignore that and get a completely different answer. Okay, Yeah, so with the dot in the bottom level or in the middle. Okay, two different things. Okay, good. So how about a few more? Let's do like three more. So d over dx. Let's say 2 square root x. Do you need a parenthesis here? Yes. Okay. Now we're going to use the power rule. So that means first we take the 2 out and then use the power rule. So we can write this one as x to the 1/2 with a square root. Now we use the power rule. So 2 times, if you take the derivative of this, so we can see it is 1/2 x to the negative 1/2, and then you can see this and that get cancelled, so you get x to the negative 1/2. We do not write negative sign, we don't leave negative powers in the final answer, so we can write this one like that, but this simply means 1 over square root x. Okay, so that's the final answer, and you can skip certain steps. Okay, that's okay if you understand what you're doing. How about this one, d over dx? Let's say 7 over x to the 5th power. So, and then this is, okay, now the question, do you need a parenthesis now? And you can see that you do not need a parenthesis now. Okay, so I'm not writing it because it's not necessary here. You can, but it's not necessary because it's clear what you're doing right now. So again, what we're going to do is we're going to pull the 7 out, take the derivative of the other function, but the other function you can write as x to the negative 5. Now we use the power rule, so 7. Okay, I'm not gonna write 7 negative 5 because this looks like you're subtracting. So that means when you write a negative number, make sure that you use a parenthesis to avoid the confusion. Okay, so when I especially multiplying with a negative number, I always put a parenthesis around to avoid the confusions. And when you write the parenthesis, you don't want to say, you want to use the dot because parenthesis means multiplication around. Okay, so it's automatic multiplication, so we don't write the dot, it means multiplication. Okay, so let's do something right. Okay, x, and you subtract 1, so that means can be negative 6. Now negative 5 times 7 is negative 35, so we can write this one as negative 35, and then you know how to write the answer now. So it's negative 35 over x to the 6. Okay, so we can skip some steps. So that's the final answer. We write the negative sign in front. Okay, so I don't like if you write negative 35 over x to the 6. Okay, it's okay, but it's not simplified enough. Good. So let's do the final problem. So how about this one, d over dt? So let's say 3t. 3t. Do you need the parenthesis? Yes. T is a constant. 3 is a constant, and we have dt over dt. dt over dt is 1. So that means 3 times 1. It's not 3.1, it's 3 times 1. So this is 3. Okay. Also, you can use a parenthesis around if you want to exaggerate some multiplication. Okay. That's one way. If you forget that this is a multiplication, so you can use that. Okay. You can say, okay, times 1. So it's 3. Good. So this is how you do the take the derivative of constant functions. Okay. Constant multiple. Okay, now let's go to the next most important one. Okay, actually, what does that mean? This means that if you take the derivative, if you find the slope of this curve, what curve? So you have y equal 3t curve. So if you have y equal 3t curve, the y equal 3t, it says that the slope of this curve is 3. The slope, we normally use m, is 3. That's exactly the case. Okay, we know that's a slope. Okay, that's what it says. So derivative is the slope, and this is the justification for that. Okay, so let's do the sum rule. So what's the sum rule? Sum rule. So what the sum rule says? Sum rule says if you have d over dx, a sum fx plus gx, sum like that. So what it says that you can take the derivative of the function separately. Okay, So that means this simply equals to the derivative of the first function plus the derivative of the second function. Okay, that's a sum rule. And also the same rule even works for negative signs as well. So that means even if you have a negative sign, it still works. Okay, so if you have plus sign, go with the plus. If you have minus sign, go with the minus sign. Okay, so this is the sum rule. It's a sum rule. That's also like an obvious result. It's coming from the limit definition, why this is true. Okay, we normally prove this one in a calc 1 using the limit definition. Okay, let's do some examples. So this is like one of the very important result, very important result. So that means, for example, if you have the if you need the derivative of 5x to the fourth minus 3x squared plus 7x, let's say plus pi is a constant. Okay, do we need a parenthesis around? Yes, because otherwise you are only taking the derivative of the first term. Okay, so we need that. That means take the derivative of the everything. Good. Now what we do, we take the derivative term by term. So let's take the derivative of the first term. It is 5 times, and then constant is 4. So what's going to happen? Erase this. What's going to happen is 4 times x to the 3 minus 3. The next power is 2, so it is 2x to the 1, and then plus 7, and we know that the derivative of x is 1, and then pi is a constant, so it is 0. Okay, so that's what happened. Now if you can simplify, so in this case we can simplify 5 times, so it's a multiplication, so it is 20, x to the third power, 3 times 2 is 6x, we don't write x to the 1, plus 7. So that is the final answer, most simplified answer. Okay, very simple. So let's do more. How about this problem? So let's say we have d over dx. Let's say 9x to the fifth power minus 4. Just put some numbers, 3, and then let's say x to the fourth power fifth root. Okay, something like that. Again, there are more terms, so we need a parenthesis. Okay, good. So if when you see terms like that, the first thing is you try to write using powers. So let's do that. So this is already there, so we can repeat it. And this one we can bring the power to the top, so it's going to be negative 3. And then plus here, you can see fifth root means 1/5 power. That means it's going to be x to the 4/5. Okay, that's the first step. You don't take any derivatives, just rewrite using the powers. Now we can use the power rule. Okay, so let's use the power rule now. So according to power rule, it is 9 times 5x to the fourth minus 4 times power is negative 3. So negative number, so I'm going to use a parenthesis to avoid the confusion. And x subtract 1, this means negative 4 plus the power is 4/5, it's clear. And next you subtract 1. So what's going to happen? When you subtract 1 from 4/5, so it is negative 1/5. Okay, is that clear? So now what we can do is we can simplify this further. So when you simplify, you're gonna get, and if it is not clear, like how to get this one, I'm gonna show you that work here. So so what we can do is, so what we are doing here actually, so I'm just a note, okay, a simple note of what's going on here. So we have 4/5 minus 1. So what we normally do is you take the common denominator. The common denominator in this case is 5. So we can multiply the top and bottom by 5. So we can write this as 4/5 minus 5 over 5. And then after that, you just need to subtract the numerators. So that means 4 minus 5 is negative 1 over 5. But we don't write the negative sign there. So we write the negative sign in front. So that's why you get negative 1/5. Okay, good. Yeah, I think I take too much space. So now I'm gonna write the final answer here. I'm gonna skip it that part. So you're gonna get 9 times 4 is 45. X to the fourth power minus actually it's a negative 4 times negative 3, that means positive 12. So it's 12, and then you can see this is a negative power. It's gonna go down, so that means it's gonna be x to the fourth power. And again, we have negative 1/5, that means it's going to go down, positive 1/5, that means fifth root. So you can write the final answer as 4 over 5 times the fifth root of x. Make sure that you put the 5 in the basket. Okay, good. So that's the final answer for that. Good. So this is like extra. I'm gonna take this part out. Okay, that's just a simplification. Okay, good. So that's how you use the sum rule. Okay. So let's do one more problem that seems like it's not the simple rule, but it is. Okay. So for example, this problem. So this is especially useful in Calc 2. Okay. We can discuss that later. So this problem, d over dt, d over dt. Let's say we have t squared minus 2t plus 3 over t square square root. In this case, you don't need the parentheses because it's a quotient, so we just leave it like that. Okay, writing parentheses around this is really unnecessary. Okay, I should say it's like bad practice. Okay, so let's not do that. Okay, only write when it is necessary. Okay, so or it is not clear. Good. So you can see that we tried to the derivative. Maybe if you know the quotient rule, you feel like you're going to use the quotient rule, but you don't need the quotient rule for this problem. Especially this is very important when you try to take the integrals. Okay, we can do problems like that, because when you take the integrals, there are no quotient rules for integrals. Okay, you definitely have to use the method that I'm discussing here. Okay, so this is very important in that sense. So let's put an arrow here. Okay, special problem. I'm gonna kind of point out this problem in the description, okay, with the timestamp. Okay, so what you do first is you divide each term. That's the first thing we do. Okay, so we're gonna divide first, so we don't do anything with this. We're gonna divide. So it is t squared over square root t minus we have 2t divided by square root t, and then plus 3 over square root t. Now we have more terms, so we need the parentheses now. Good. So let's simplify this first. So we can divide. That means you're going to subtract 1/2 from the numerator, the power of numerators. So that means this can be t. You subtract 1/2, so it's going to be 3/2. And then minus 2 times, if you subtract 1/2, it is t to the 1/2. And then this is 3, the t to the 1/2 it comes to the top, so it's going to be a negative 1/2. So that's what happened. More terms, so we put the parenthesis around. Okay, now we can see each term has a power, so we can use the power rule. So if you use the power rule as a d over dt, so this is no, we don't need that because we're gonna use the power rule now. So let's use the power rule. So it's gonna be 3/2 t subtract 1/2, that means 1/2 minus 2 times power rule 1/2, that's the power, t subtract 1, so negative 1/2 plus 3, the power is this, so subtract that, so it is negative 1/2. It's a negative number. I put a parenthesis just to make sure there's a multiplication, and t, now you have negative 1/2. When you subtract 1 from negative 1/2, it's going to be negative 3/2, right? Again, if you forget how that's going to happen, so you can see it is 1/2 minus 1, take the common denominator, so it is 1/2 minus 2 over 2. That means negative in the top is going to be negative 3 over 2. We can write this like that. Okay, so we can write this one as negative 3/2. Okay, these two numbers are different. The first one says negative 3 divided by 2. The bottom one says is negative 3/2. So those are two different numbers. Okay, good. Now we're gonna write them use proper notations. So let's do that. So if you use proper notations, you're gonna get 3/2 square root t, and then this get cancelled, so you get negative. So negative power go down, square 1/2 means square root, so it's gonna go like that. And then this also, there are some simplifications, so it is negative 3/2. I'm gonna write this in different way now. Again, go down, half means square root, so that means you can write this one as 1 over t cube square root. Okay, so that is the number using the radical notation. Good. So that's the final answer for that problem. Okay, it's not difficult, but there are certain things that you need to remember. Good. Now we're gonna talk about one of the most important results, what we call the product rule. So let's do the product rule. So let's do the product rule. So product rule. So what the product rule says? It says that d over dx, you have u and v two functions. When you have product, you need to put the parenthesis. Okay, and then what the result says, it is u v prime plus v u prime. So it doesn't matter which one you write first, just remember whatever form you like, but you can, only thing that you remember is you only take the derivative of one of them and multiply by the other one itself and have a plus sign. Okay, plus sign. Good. So you're gonna get this one. This is what we call the product rule, u v prime v u prime. Okay, so that's how we remember, u v prime v u prime. Okay, u v prime v u prime. So good. So let's do some problems. Okay, so let's start with one of the products. Let's say d over dx. So we have product, so that means you need a bracket. And also try to use the proper brackets. So don't try to use brackets when you want to use parentheses. For example, in the first one, I don't write d over dx bracket uv. Okay, it's not really proper because there are levels of those brackets. For example, we use the parentheses as the smallest case, and then we write this as the next one, and then this is the largest one. So those are the kind of levels that we go from. So we don't use square bracket when you want to use a parenthesis. So we don't do that. Okay, so that's the kind of priority order for those. Yeah, that's what we call the proper writing. Okay, yep, good. So that's why we use the bracket here now, because that's in the next level. Good. Now we can see, so that is the u function. This is the v function. It does not really matter. Just pick one as u function, one as the v function. Okay. Good. So I'm going to use the product rule now. So what the product rule says, write the first one as it is. Take the derivative of the second one. So I'm going to use the prime notation now. So prime, when you see the prime, that means take the derivative of whatever inside. Plus, switch the order. What do you write the v now? So v and u prime. What is u? x3 plus 1 prime. When you see prime, that means the derivative. This is u v prime, v u prime. So let's write. So is u v prime and then v u prime. Okay, so that's what happened. Now what we can do, we can take the derivatives. Okay, so we do, and then remember the plus sign. So it's very important as a plus sign. Okay, plus, because when it comes to the quotient rule is a minus sign. Okay, good. And I will tell you how to remember that as well. There's a easy way to remember this. That. Okay. Okay. Now let's find them one by one. So I'm gonna leave this and take the derivative. So what's the derivative of this one? For x. Okay, because it's 2x squared, so it is 4x and plus 1. Here you repeat and then take the derivative, so it is 3x squared plus 0, we don't write that, okay, 3x squared. Okay, now what do you do? Don't leave it like that, okay, just try to expand and simplify. So when you expand, what do you get? So we're gonna first multiply the first term by everything. We explained this in the algebra video, how to expand like that. Pick one term, multiply with everything. Pick the next term, multiply with everything, like that, okay? That's how we do. So pick the first term, multiply with everything. So what you're gonna get is 4x to the 4th power and then x to the cube. Now we pick the next term, multiply, so you're gonna get 4x and then plus 1. So that's what you get from the first one. If you go to the second one, do the same thing. Pick one, multiply with everything. In this case only 1, so it's easy. So you have 3 times 2 is 6, x to the 4th power plus 3x to the cube. Now collect terms. You can see you can combine. So you can see you can combine these two and those two. Okay, so let's combine them and write the final solution. So we have 10 x to the 4th power plus 4x to the cube plus 4x plus 1. So that's what you get as the final answer. So let's do one more. The next one. So let's do a little complicated one. Okay, so d over dt, t square root 3t to the 4th power minus 1. Again, more terms, we need the bracket. More than one term. Again, the u function, it doesn't matter which one, okay, just pick one. Because you just take the derivative of one, multiply with the other one, and take the derivative of the other one and multiply. So it doesn't matter. That's why it doesn't matter, okay, because it's a plus sign. Okay, so I'm going to rewrite the first one as it is. Take the derivative of the second one. So if you take the derivative, so let's write. And it's okay to write this step because sometimes it's going to save a lot of points because sometimes we forget what we are doing. And so it's okay to write this, okay? Even if you don't write, that's okay, but that can save sometimes. Okay, now let's do what we are saying. So take the derivative. So if you take the derivative, you're going to get 12t3 minus 1 means 0, so we don't write it, plus 3t to the 4th minus 1. Take the derivative. So this is a half power, so that means 1/2 t to the negative 1/2. Now multiply through. So what's going to happen here? So you can see t to the 1/2, t to the cube. So you're going to add 1/2 to the cube. So if you add 1/2 to the 1/2 to the 3rd power, how much you get? If you add 1/2 to the 3rd power, so I'm going to do the work here. So we have 1/2 and a 3. So take the common denominator. Common denominator is 2. So you can multiply the top and bottom by 2. It's going to be 6 over 2. So that means 6 plus 1. So that means 7, 2. Okay. There's another way to do this problem. What normally happen is this. You multiply these two and add that. Okay. That's what happens. So multiplication and addition. Always. Okay. When you have a fraction and a number, you multiply with the denominator and add to the top, so you get the number. Okay, it works anytime. And if it is a subtraction, like for example, the next one you have 4 negative 1/2. In that case, you subtract, you multiply and subtract. Okay, that's what can happen. Okay, so we do more. Okay, so when you do that, that means you're gonna get here 12 t to the 7/2. That's what you get. and then the same argument. In the next one, you have to multiply by 1/2 t to the negative 1/2. So that means the number is going to be 3 halves. So it is t to the 4th. That means 4 minus 1/2. How much 4 minus 1/2? If you do 4 minus 1/2, you can see that's again 7/2. Okay. Again 7/2. And then you have the next one is you multiply by -1. So that means you can write this one as 1 over 1/2 means you can write 2 like that, and then -1/2 positive 1/2, so it's square root t. So they get. Okay. Now you can combine these two. You can see we have 12 and 3 halves. So we can do the same argument. So you add a term to you add an integer. Okay, let's do work here. To have an integer and a fraction, it is an addition. Very simple. You multiply these two and then add to that. So multiplication and addition. So that means you're gonna get 12 times 2, 24 plus 3 means 27. So that means it is simply 27 over 2. Okay. So that means when you add these two numbers, you're gonna get 27 halves t to the t to the 7/2. Okay, t to the 7/2. That you can write as, how you can write that? So you can say you get 7/2. That means you're gonna get the 27 power. 7/2. 7/2 means you're gonna get the square root of t to the 7. So it is t to the 7 and the square root. Okay, so to get negative 1 over 2 square root t. So that's the final answer for that problem. Okay, it's not that difficult, but there are some algebra that you need to remember. Good. So let's do maybe one last problem which has a little bit more terms. So how about this one as the last problem of this type? So it's a d over dx. The product 2x plus 3, and then we have x squared minus x plus 1. Okay, good. So this is easy. Again, we have a u and a v. So what do you get? You write the first one as it is. Take the derivative of the second one. So it is 2x minus 1. And then write the second one as it is. Take the derivative of the first one. So it is 2. Okay, now we are done with the derivative part. It's just algebra. So multiply through. We multiply the first term with first term. So you're going to get 4x squared. And multiply the second one. So you get negative 2x. Now we multiply and the second term with the first one. So you get 6x and then minus 3. Here you're going to get 2x squared minus 2x plus 2. Now combine like terms. So if you combine like terms, you get 6x squared, and then you get negative 4 positive 6, so you get 2x and then minus 1. So that is the final answer. Okay, so next what we're going to do, are we going to do more complicated problems later after we know the chain rule and other results. So let's move on to the next result, the quotient rule. Before we discuss the next topic, let's try to look at one of the problems that we did before, again using a different technique. So for example, we look at this problem before using the product rule. So we had d over dt square root t 3 to the t4 minus 1. So this problem. So you know that we normally do, because you see a product, we normally do a problem like that using the product rule. But there is a way to avoid the product rule for these kind of problems, and you can get the answer much quicker. So what we're going to do, we're going to distribute this first, because you can multiply by square root t, the two terms, and we're going to distribute that first. So if you do that, so what are you going to get? D over dt. So we're going to multiply through. So we're going to multiply by t to the 1/2. So that means you're going to get 3 t to the 4 and plus 1/2 minus t to the 1/2. So if you simplify, so we are not taking derivative yet. So if you simplify this further, you're going to get 3. If you add 1/2, this becomes 9/2 minus t to the 1/2. And you can see that this is very simple. So you don't need the product rule for this one. So just take the use the power rule and get the answer. So you can see this is much quicker. So it is 3. If you use the power rule, it is 9/2 t to the 7/2 minus what happened here? It is 1/2 t to the negative 1/2. So we can write this using the radical notation. So that means your final answer is going to be 27 over 2 t 7 square root minus 1 over 2 square root t. So you can see you can get the answer much quicker, and you do not need the product rule for this problem. So there are certain things that you can do to make the algebra simple. Okay, so you can do similar things again when it comes to quotient rule. So let's discuss the quotient rule now. So the quotient rule. Quotient rule. So what's the quotient rule? So we have the derivative of a quotient. We normally write uv. That's the standard format we write, u over v. Again, when you have a quotient, you don't need the parentheses, but I just write it just to make it clear. Okay, and then what's the formula? How you remember? The v comes first. So remember that v comes before u. Okay, v comes before u. So it is v u prime minus, there's a minus sign, u v prime over v squared. So it's a prime notation for derivatives, and this is how you write. That's why the order matters, because there's a minus sign for the quotient rule, there's a plus sign for the product rule. So if you change this to the plus sign, and if you remove the denominator part, that's just the product rule. But for the quotient rule, there's a minus sign, and v comes first. Okay, so v comes first. So that's the product rule. So again, how you remember this? Remember v comes before u. Okay, so remember that. Okay, so in other words, so this v means v, and this u means u. Okay, so so v comes before u. Okay, so remember that. That way you can remember the formula is never gonna, you never forget that. Okay, so let's do the first problem. So the first problem is d over dx. So let's say we have x plus 2 over x minus 1. And in this case, you don't need a parenthesis because it's a quotient. So we are not going to write the parenthesis for this one, and it's clear. So, so according to the product rule, and then you can, according to the quotient rule, so we're going to consider the top, that's the u term, that's the v term. So let's write it. So v u prime, v means x minus 1, and then u prime. Since this is the first example, I'm going to write it like that. So the prime notation minus u, that means x plus 2, v prime, x minus 1 prime, over v squared, so x minus 1 whole thing is squared. So now let's try to take the derivatives. If you take the derivatives, it is x minus 1. A derivative of the first term is x plus 2, so derivative is 1, minus x plus 2, derivative of x minus 1 is 1, over x minus 1 squared. And then let's simplify. So now you can see it's a 1, so that means what you have is x minus 1, and then when you multiply by the minus sign, you get minus x minus 2 over x minus 1 squared. Now you can see you can simplify the top, so these two get cancelled, so you get negative 3. So you get negative 3, so we put the negative sign in front, so negative 3 over x minus 1 squared. So that is the final answer for this problem. And you can see it's not difficult, but there are certain steps that you'll follow and you remember the formula. Very important thing is the negative sign. That's a negative sign. So let's do more problems. Let's do another one. So how about this one? D over dx, 3x squared plus 1 divided by x cubed plus x. Okay, again, we don't need the parentheses for this one because it's a quotient. It's obvious what we have to do. Okay, again the formula. Vu prime, V means x3 plus x, V u prime. So it is, what's the u prime? What's the derivative of the first term? 6x. So it is 6x minus u, that means 3x squared plus 1 u, V prime. What is V prime? Derivative of the bottom term, it is 3x squared plus 1 divided by the denominator is squared, so x cubed plus x whole thing squared. Okay, now what you need to do is the derivative part is over. Now what we do is the algebra part, just a simple simplification. So let's multiply through. So you're gonna get 6x to the 4th power plus 6x squared. And then when you multiply through the next one, because there are a lot of terms, I'm gonna write using a parenthesis for that. So you're gonna get, if you multiply the first terms, so you can use a FOIL here. You see that you get 9x to the 4th power, and then you multiply the last term with the first term, so you're gonna get 3x squared. Now you multiply the second term with the first term of the other one, so you're gonna get another 3x squared, plus you multiply the last term, so you're gonna get that divided by x3 plus x squared. So now you can simplify this further. So you can see, so you can simplify the x to the 4th power. So you're gonna get negative 3x to the 4th power, and then x squared. So you can see 6x squared, and then you have negative 3 squared, because of negative sign, so they get cancelled. So and then you only get minus 1 over x3 plus x squared. What we can normally do is we can pull the negative sign out, and we can write this as a positive term, because it's much better to write it that way. Okay, so x3 plus x squared. We try to write the final answer using least number of negative signs. So that's the kind of, if you look at the solutions in the back of the book, you can see this pattern. So we always try to do that. You try to write your solutions using least number of negative signs, because in this way your answer only have one negative sign. So that's why we do it like that. Okay, we prefer that. Okay, let's do another one. Like this. So let's say d over dt t squared minus 1 over square root t. Okay, again, no parentheses needed. So we just use a result. So it is vu prime minus vu prime minus uv prime. Okay, so u, that means square root t, vu prime, so it is 2t minus u, that means t squared minus 1. V prime means 1/2 t to the negative 1/2 divided by t square root squared. You can just write t, that's okay, but I'm just writing showing all the steps. Now let's simplify, let's multiply through. So when you multiply through, you're gonna get from the first term t, you have a half power, 1 power, that means t 3 halves, and you add them. And then again, when you now we're going to multiply through the other two. So you're going to get from the first term, you get 1/2 t squared negative 1/2, that means you subtract 1, so you're going to get t 3 halves for that. And then negative positive, so you have 1/2 t negative 1/2, and in the bottom you're going to see t. Okay, now what we can do is we can simplify a little bit further. So what we can do is this is, you see, a 1/2. So what I'm going to do, I'm going to multiply t 2 Also, you can see t to the negative 1/2, so we can multiply by the opposite sign. That means, so we find the smallest term and multiply by the opposite sign. So we can multiply the top and bottom by 2t 1/2. Because the reason is you try to cancel that term, so we can multiply by the opposite sign. So once you do that, as you can see, so 1/2, so 3/2, that means you're going to get added up. That means t squared become t squared, and then 2 minus 1/2 means 3/2. And also, actually, you multiply by 2. So when you multiply by 2, 2 become 4, 1/2 become just 1. So that means 4 minus 1 become 3. So that means your final answer is 3t squared minus 1 over 2 t to the cube square root. So that's the final answer for this problem. Okay. So if you find any difficulty at any place, what you can do, you can put that in the comment section. Either me or someone else will answer that. Because there are a lot of very generous students and they can help you as well. Okay, so let's do the last problem of this type before we move on to chain rule. So how about so let's do one last problem before we move on to the chain rule. So how about the function s, which is square root t over 1 plus square root t. Okay, that's a function. So the derivative ds over dt. Again, we use the quotient rule for that. So if you use the quotient rule, v, that is 1 plus square root t, and then vu prime. So we can take the derivative of the top term. So that means 1/2 t to the negative 1/2 minus u v prime. And when you do v prime, and you can see 1 is a constant, so that means you again get the same term t negative 1/2 divided by 1 plus square root t squared. So let's see how the simplification works. So what's going to happen when you multiply through, so you get the first term. So the first term is simply 1/2 t negative 1/2, and then what's going to happen when you multiply through, this is negative 1/2, this is here we have positive 1/2, so when you multiply through they get cancelled, so you simply get 1/2 from the second term. And the same argument works for the last term as well. Square root 2 cancel with square root t cancel with negative 1/2, so you're going to get negative 1/2 t negative 1/2. Same argument, because this is positive 1/2, this is negative 1/2, they cancel. So that means you're going to get negative 1/2 divided by 1 plus square root 2t squared. Now you can see these two terms get cancelled. So you're going to get 1/2 t square root. So what we can do, you can multiply the top and bottom by 2. So you can multiply the top and bottom by 2 times, by 2 to cancel 1/2, 2 times square root t, okay, top and bottom. So once you do that, you're gonna get this answer as the final answer. So that means top is simply gonna be 1, the bottom is 2 square root t 1 plus square root 2 squared. So that's the final answer for this problem. So it's very clear. Okay, good. So so we're gonna move on to the next topic. What we can do, we're gonna do the chain rule. Okay, do the chain rule. That's again one of the very important topic in calculus, because that's everywhere. Especially for calc 2, we need chain rule a lot. Okay, so chain rule. So chain rule, so what we're gonna do in the chain rule is we can assume that there's a function u, so which is a function of x. So that means u is a function of x. Okay, so that means it's a function of x. That's how we write it. U is a function of x. So if that is the case, what's going to happen if u is a function of x? Let's say you need to take the derivative of a function where uh, you have another function which is a function of u. Okay, so let's say you have a function which is a function of another function of a function. Okay, the composite function. Now the goal is, what is the derivative? So you have a composite function, you try to find the derivative of a composite function. So what the theorem says that in this case, what you normally do is you just take the derivative of the function f with respect to u first, and then take the u with respect to x. Okay, so that's what we call chain rule. Um, this also equals to what we do is you take the derivative of f with respect to u times the derivative of u with respect to x. So that is another version of the chain rule. Okay, so let's see how we're going to use this. This is a very simple idea. So this is what we call the chain rule. Only condition is u has to be a function of x. Okay. So what we normally call this u is what we call the inside function. Okay, so we call so u is what we normally call the inside function. Okay, inside function. So the goal is to find the inside function. Okay, so this is, so it works for composite functions because a function of a function. Okay, so works for composite functions. Works for composite function. Okay, so when you have composite function, we can use the chain rule. It's a function of a function. Okay, so let's start with and then also we have what we call the general power rule. So we can use the so let's try that also. So the other version is the what we call general power rule. General power rule. So what's the general power rule? It's the derivative of a, let's say you have function to the nth power. So what general power rule says that simply treat fx as x, so that means this simply become n fx to the n minus 1 times you have extra term f prime x. So if you remember this one, this is really helpful. This is what we call a general power rule. So if you see any function to a power n can be any number, any constant, then your answer is simply going to be n fx n minus 1, and then you multiply by the derivative of the function. So this is what we call the general power rule. You can see it's very similar to the power rule, except that extra term f prime x in there. So we call this is a general power rule. Okay, that's that extra term. So this is important. Okay, so so let's try to do this problem. So let's try to do some problems until you get comfortable. So we can do a little bit more problems from this one because this is like one of the very important topic. So let's start with this problem. So let's say d over dx x cube plus 1 to let's say fourth power. Yeah, some numbers. So, and then you can see that you can directly use the general power rule for this problem. So if you use the general power rule, what's going to happen? So in this function, fx is simply the inside function, x cubed plus 1. According to general power rule, this is simply going to be n equal 4. So that's the n value, that's 4. And that's the fx function. So you can see this is simply 4. Write the function as it is. Subtract 1 from the power, so it's going to be 3 because n minus 1 times multiplied by the derivative of the function. So d over dx, derivative of the inside function, x3 plus. That's it. That's the general power rule. So that means 4 x3 plus 1. You can see there's nothing happening inside. And if you take the derivative, this is simply going to be 3x squared. Now what we're going to do, we're going to multiply through. So when you multiply numbers, you multiply the numbers first. So 4 times is 12 and x squared, and then we have x3 plus 1 to the third power. And you can see you can do 1,000 problems like that. It's very simple, very simple. Now, so if we use the chain rule the other way, so let's do this problem using the other technique also. So what's gonna happen? So we have x3 plus 1 to the cube, and what we can do, we're gonna take a u. So what is u? U is the inside function, in this case x3 plus 1. So now let's try the formula. According to the formula, what we're gonna do is, so this simply becomes d over dx u to the cube. So that's what happened, because u is the inside function. Now according to the chain rules, that's where we're gonna use the chain rule. Okay, according to the chain rule, this is gonna be um, d over du u cube, because that's a function, okay, times du over dx. Okay, so this is coming from the chain rule now. Okay, so that's the chain rule. Not the power rule, the chain rule. So now, according to the formula, so what's going to happen is you take the derivative of this function with respect to u, this has been 3u squared, and take the derivative du of u with respect to x, so that means 3x squared. Now what we can do, we can replace u back. So actually, I'm sorry, I changed the problem, so this should be 3. So okay, so this is actually 4, this is the same problem. So 4 and 4. So what happens? 4. So we have 4 u cube. Okay, good. Now what we're gonna do? We're gonna substitute for u. So if you substitute for u, what's gonna happen? It is 4 u simply x3 plus 1 cube times 3x squared. If you multiply through, you're gonna get 4x squared x3 plus 1 cube, and you can see that these two are the same. Okay, so these two are the same. But if you get a problem like that, the general power rule will be much faster. So especially you have some function to a power, so just try to use the general power rule. So what's the general power rule? N fx to the n minus 1 times the derivative of the inside function. That's the general power rule. It's much faster. Okay, so so let's use general power rule for this problem. Okay, so you can see it's much faster and quicker. So this problem. So let's say we want to find the derivative of 3x squared minus 4x plus 5 square root. Okay, so that's the problem. So what you're going to do, you're going to figure out what is n in this case. So you can see this is simply, you can rewrite this. This step is not really necessary, but if you want to make it clear, you can write that. So it's 3x squared minus 4x plus 5 1/2 power. Okay, now we use the general power rule because you see the function right there. So according to general power rule, it is 1/2, that's n, and then 3x squared minus 4x plus 5 negative 1/2, so that is n fx n minus 1 times the derivative of the inside function. So what's the derivative of the inside function? 6x minus 4. Okay, very simple, just one line. Now what we're gonna do is, you can see 1/2, so you can cancel 2, and this is gonna be 3, this is gonna be 2, so that means you can write your final answer, and also you can bring the negative 1/2 term down, so that means your final answer is gonna be 3x minus 2 over 3x squared minus 4x plus 5. So you can see that this is much quicker. Okay, it's much quicker, and that is the final answer for that. So if you want to find the tangent line for a curve, for that curve, this is exactly what you do. We simplify like that, and then we're gonna plug in the values and find tangent line. Okay, good. So let's do a problem like a product problem now. So how about this problem? So let's say we have d over dx, x plus 1 squared, and then we have x squared plus 2x, something, you know. So this is a product, so we need another, so we put the bracket there. Okay, now what we can do, we have to use a product rule, and you can see, so that's the u term, that's the v term. So u term is everything. Yeah, I'm gonna write it like that. So it will be, we're gonna make sure what is the u term. So u term is everything including the power. V term is this one. So that one does not power. So okay, so let's use the product rule. uv prime vu prime. So this is the product rule. I'm gonna write the first term u, no change. V prime. So we write x squared plus 2x prime plus v, that is 2x plus 2x, u prime, which is x plus 1 square the prime of that. Okay. So for this one, for this, we're gonna use the chain rule. Okay. So use chain rule. So inside the product rule, you have to use the chain rule. Okay. Only for that you have to use the chain rule. So let's use that. So if you use it, now we're gonna find the derivative. So it is x plus 1 squared. The derivative is 2x plus 2 here, plus x squared plus 2x. Okay, now let's use the chain rule. So we use the general power rule again. It is 2 x plus 1. You subtract 1 from the power and then multiply by the derivative of the function inside, which is 1. Okay, so that's what you get from the general power rule. Okay, so this is general power rule. Yeah, so this part is coming from the general power rule. Okay, so now it will be best to simplify these kind of one using factoring methods. Just try to take the common factors out. So if you take the common factors, what are the common factors? 2 is a common factor, x plus 1 is a common factor. So if you take the common factors out, from the first term you're going to get x plus 1 squared, because you took this term out. In the other one we take 2x plus 1 out, so you end up getting x squared plus 2x. So to get, now we can simplify again that part. So we have 2x plus 1. Okay, so we first use the foiling for that one, and if you look at the factoring polynomials video, and you can see that you're going to see a lot of formulas there. So this is like one of the squaring formula. So this is square of a binomial term. Okay, we know the formula for binomial, squaring of a binomial. So if you use that, or you can use the foiling for this one. So if you use the formula, what do you get? X plus 1. You can write this one x plus 1, x plus 1, expand. So you simply get, you square the first term, twice the product. So you're going to multiply 2 and multiply by 2. So you get 2x, and square of the last term, that means 1. That's what you get when you expand that. Okay, that's what we call the complete square of a binomial term. So you can use the Pascal triangle for that. 1, 2, 1. So those are the coefficients. 1, 2, 1. See, numbers 1, 2, 1. The coefficients. Okay, now we write the rest. So x squared plus 2x. So that's what you get. Now we're going to collect the terms. So you get 2, we have x plus 1, and then we have 2x squared, and 2x means 4x plus 1. So you can factor this further, so we can leave this as the final answer. You know, this algebra takes some time, but the derivative doesn't take much, but the algebra takes some time. But what I'm going to show you, inside the problem you use the product rule and the quotient rule. Okay, both of them. Okay, so let's try to another problem using the chain rule and the quotient rule. Okay, so how about that? So the next problem, so we have d over dx, let's say x plus 1 over x minus 1 square root. something like that. Again, so for this problem you can use a general power rule, because you can see this is a function to a power. So you can see this problem looks like this. You have some kind of function uh, and a power. Okay, in this case n equal 1/2. So we can use a general power rule for this problem directly. So we can write this one as d over dx, x plus 1 over x minus 1 to 1/2 with the square root. So let's use a general power rule now. According to general power rule, 1/2 x plus 1 over x minus 1 negative 1/2, okay, n fx n minus 1 times the derivative of the inside function. So the function is x plus 1 over x minus 1. For that we use the quotient rule. Okay, so we leave it like that. So 1/2 x plus 1 x minus 1 negative 1/2. So let's use the quotient rule. So it is v u prime minus u v prime over v squared. Okay, so you can see that's the u term, that's the v term. Don't change the order. So the formula was v u prime u v prime over v squared. That's the quotient rule. So it's a quotient rule here. Now we're going to simplify this a little bit. We still don't do anything with the actually what you can do, you can now expand this one. So we can write 1/2. So we can write this one as x plus 1 to the negative 1/2 power x minus 1 to the negative 1/2 power. You can write it like that. You can break it into two. So let's simplify the top. So when you simplify the top, what happens? You can multiply with negative sign. So you get negative x negative 1. So that means x and negative x get cancelled. So these two get cancelled. So you get negative 2 at the top. Okay, so you get negative 2 divided by x minus 1 squared. Now you can see further simplification. So you can see these 2 get cancelled with that 2. So you only get negative sign, and also in the bottom you can combine the 2. You have negative 1/2 power. You have a negative 1/2 power, and then we have 2, so that means you're going to get 3/2. Okay, so that means the bottom simply going to be so bottom simply going to be so it's a negative. So bottom simply going to be so x plus 1 negative 1/2, you can bring it down, so that means it's going to be x plus 1 to the half power, and the other one simply going to be negative 1 to the 3/2. All right, you have a 2 and a negative 1/2, so you're going to combine these two, so you're going to be 3/2. Now we can use this using the radical notation, because 1/2 means the square root. So you can combine, you can take the 1/2 power as a square root, and you can combine the other two. So that means you can simply write this one as negative 1 over, you can combine the two, so it is x plus 1, x minus 1, you can write this one as a cube and a square root. Okay, so that's the final answer. So what happened here? So we use this property. So if we have x3 square root, so this is simply x3 halves. Okay, so that's the idea. So you can write it like that. You can put the power inside, the root outside. Okay, so for example, if you have y to the 7th is the root, y 5th is the power, so that means it is y to the 5th, the 7th root. Okay, so that's the kind of idea. Okay, so you can see, I mean, you need a little bit of algebra to simplify this problem. Okay, but the calculus part is not that difficult, so that comes like easily, but you need some algebra to completely simplify the problem. Good. So that's about all those major types. Now what we're gonna do, we're gonna cover the other functions. For example, what are the formulas for trigonometric functions? What are the formula for exponential, logarithmic, inverse, trig, and hyperbolic functions? So let's talk about that now. So next we're gonna do the trigonometric functions. Okay, so trigonometric functions. trigonometric function. Good. So what are the formulas that we have? So we have d over dx sine x, d over dx sine x, which is equal to cosine x, and then d over dx cosine x, which is equal to negative sine x, and then d over dx tan x, which is equal to secant squared x, and then we have d by dx cotangent x, which is negative cosecant squared x, and then we have d by dx secant x, which is secant x tan x, and we have d by dx cosecant x, which is negative cosecant x cotangent x. And how to remember? And you can see that all these functions on the right side has a negative sign c in front, and all those functions are negative. So that's how you remember. You can see the functions with the c in front has a negative sign in the derivative. The other functions are all positive. Other functions are all positive. Good. And then yeah, we can talk about the hyperbolic functions also. So so let's talk about that. Do later. So let's have this one in a box. So these are the uh, formulas for trig functions. Okay, so let's start. Let's do these problems. So let's say the derivative of 2 sine x. We know that 2 is a constant, so we take it out. And according to the table, derivative of sine is cosine x, so that means 2 cosine x. The next one, let's say d over dx 4 secant x cube. So you can see that this is not just x, is x cube, so that means you have to use a chain rule. So this is simple. We know that 4 is a constant. So derivative of secant is secant tan according to the formula. So that means this is going to be secant, no change, and tan, no change, and then multiply by the inside function, derivative of the inside function. So in this case, which is 3x squared. So we multiply by that. Just to avoid confusion, we normally bring it in front, and then we can write, you can leave the final answer as 12x squared secant x cube tan x cube. Okay. So the next problem. So let's say we have d by dx tan square root x. Again, we have to use the chain rule. Actually, I forgot to tell you. So that's coming from the chain rule. Okay. So same thing, you have to use the chain rule again because this is not just x. So let's do the chain rule. First, this is a tan function. If it's a tan function, we know it is secant squared, so we write that first. So it is secant squared square root x, no change to the inside function, and then multiply by the derivative of the inside function. So that is 1/2 x to the negative 1/2. We have a square root function, and then we can simplify this. How to simplify? You can bring the x square root down to the denominator. So that means this is going to be secant squared square root x divided by 2 square root x. Okay, so that's the derivative of that function using the chain rule, and this is where we use the chain rule. We multiply by the derivative of the inside function. So, and you can see that there are no changes to this function. Okay, no changes. See, the sitting excellent. It's the same thing. No changes. Only you multiply by the derivative of the inside function. That's the only part coming out. You have the extra term multiplied by the derivative of the inside function. So let's do more. How about this one? So let's say we have d by dx cosecant x squared plus 3x. Okay, again, just follow the table and see what's the derivative of the major function, which is a cosecant x. So cosecant means negative cosecant. You just repeat the inside function without any changes times cotangent, again no changes to the inside function, and then we can multiply by the derivative of the inside function, so it's x squared plus 3x prime. Okay, that's the chain rule part. Okay, so it is negative cosecant x squared plus 3x cotangent x squared plus 3x, and then you can see here we have the derivative is 2x plus 3. So that means the final answer is negative. We normally put that in front to avoid confusion, and then cosecant x squared plus 3x cotangent x squared plus 3x. Okay, so that's the final answer for that. How about these two special problems? So let's do the derivative of sine squared x. So what is this? This you can rewrite if you want, just to make it clear. This is sine x squared. So this is a general power rule situation. You have function and a power. Okay, so according to general power rule, this is simply going to be you can see 2 sine x to the first power according to general power rule, and then multiply by the derivative of the inside function. So that, and then you multiply the derivative of the inside function, that means the derivative of sine x, that's the inside function. So what you get is 2 sine x, that's the first power, and derivative of sine is cosine x. Now we know that there's a formula from trigonometry which says that sine 2 theta equal to sine theta cosine theta. According to that, this is simply going to be sine 2x. Okay, this is simply going to be sine 2x. The formula that we use is that the sine 2 theta equal to sine theta cosine theta. Okay, so we use that formula. Okay, so now let's do this problem. So I'm going to slightly change the problem. Let's say we have sine x squared. Now this is actually easy. So what you're going to do is, sine means cosine, so it's a cosine x squared, no change, and then multiply by the derivative of the inside function, which is 2x. Just to avoid confusion, we write 2x in front, so it is 2x cosine x squared. So you can see that is simple, and you get completely different answers for those two. Okay, so please make sure that you understand the difference between the two. And then how about this one? So d over dx x squared sine x. So you need the parenthesis here. So we use a product rule here. So for the product rule, uv prime plus v u prime. Okay. So we assume that the first one is u and the next one is v. Okay, good. Now let's find the derivatives. So the x squared derivative of sine means cosine x plus sine x. Derivative of x squared is 2x. Now what we can do, just move terms around. You can do much here. So it is x squared cosine x plus 2x sine x. Okay, that's what get. So let's do maybe like 3 more little complicated examples. Good. So how about this one? Let's say we have d over dt secant t plus tan t to the 5th power. Again, it's a general power rule problem. So you have a function to a power, so we can write the power. Then secant t plus tan t, you subtract 1 from the power and then multiply by the derivative of the inside function, which is secant t plus tan t. So we have 5 secant t plus tan t to the 4th power. Now we're going to take the derivative of these functions. Okay, so what are the derivatives? Secant. Derivative is secant tan, so the secant t tan t. Derivative tan means secant square t. See whether we can simplify. Actually, what we can do is we can factor secant x out. So we have 5 here, and then we have secant t out as a factor. So we're going to get secant t plus tan t to the 4th power. Once you take secant out, you're going to get tan t plus secant t. So that's exactly matched with the other term. So that means you can combine the two. So you have 5 secant t plus tan t to the 5th power. Okay, so that's what you get as the final answer. Let's do maybe 2 more. How about this one? D over dx 2 sine squared x minus tan squared x. And you can see for both of them you have to use the chain rule. Because sine is squared, you can have sine x squared, tan squared, you can have tan x squared. Okay, after writing that, from the first term you get 2 times 2 sine x times the derivative of the inside function, which is cosine x, minus same thing 2 tan x is the 1 actually, is the first power, here also first power, and then the derivative of the inside function, which is secant squared x. Good. I mean, you cannot do much here, so we just simplify slightly. So what we can do is actually we can combine these two. With 2 sine x cosine x, that is sine 2x, the double angle formula. So this can be 2 sine 2x according to the double angle formula minus, here we just leave it, 2 tan x secant squared x. Okay, other way to write this one is you can write this one as 2 sine x secant cube x, but just the same thing, not much. Okay, so let's do one last problem. So let's say we have d over d theta 2 theta sine theta square root. Again, this is a general power rule problem. So you can write this one as d over d theta 2 theta sine theta 1/2 power. So according to the general power rule, this is 1/2 2 theta sine theta negative 1/2 times the derivative of the inside function, which is 2 theta sine theta. Okay, so use the product rule for that. So if you use the product rule, so 1/2 2 theta sine theta negative 1/2. From the product rule, you take the derivative, you write, you take the Actually, before we do that, we can do a simplification here. So what the simplification is, you can see that you can cancel this 2 with that 2. Okay, so that means after we remove that, you can have a little simplified version here. So that means you're gonna get 2 theta sine theta negative 1/2, and then what's gonna happen here, you only have theta, so take the derivative, that's 1, rewrite the other term, plus theta, take the derivative, that is cosine theta. So that's what you get. And then what you can do, you can bring it down and simplify, write it as just one term. So your final answer is going to be sine theta plus theta cosine theta divided by 2 theta sine theta square root. Okay, so that's what you get as the um, final answer for that. Good. So let's talk about the next topic, the exponential functions. Uh, so what results we know about exponential? There are 3 formulas for exponential functions. Um, so exponential functions. Exponential functions. So what are 3 formulas? So we have the basic formula. So it is d over dx, e to the x. If you have e to the x, we know that you get ex back. Okay, this is one of the functions where once you take the derivative, you get the same function back. Okay, that's very interesting. And then we can generalize this. So what's the general version of that? So when you have the derivative e to some function, so it's not just e but some function, so you can see this is very similar. So it is e, no change, you just repeat the function and only multiply by the derivative of that function. And then we also have one more formula. So what happened, instead of e, uh, you have some other base like a. So a to a function. So if you have a to a function, no much change, it is a to the function f prime x. We have extra term coming, you need to multiply by ln a. That's the extra term, but otherwise they are pretty much the same. And those are the 3 formulas that you need for taking derivatives of exponential functions. Okay, so there are 3 formulas there. Good. So let's try to do some problem from each type. So let's start with this problem. So let's say we have d by dx e to the 2x. So according to the formula, what you're going to do is you repeat the function, multiply by the derivative of the fx function. The derivative of that function is so derivative of that function is simply 2, so you multiply by 2. You write the final answer as 2e to x. Okay, that's the final answer. Okay, so let's do a product problem. So let's do this one. X cube ex. We need the parentheses around. So here is a product rule. According to the product rule, we write the first function, take the derivative of the second function, plus we write the second function, take the derivative of the first function. Okay, vu prime, uv prime. Now what's going to happen is x cube, we know that derivative of ex is ex again, so we leave it like that, and then we have ex, derivative is 3x squared, and if you like just rewrite this in a nice way, we have x3 ex plus 3x squared ex. That's one way to write it. And also, like when you have exponential function, you can always factor the ex term. and also in this case you can factor x squared also. So if you want, but this is okay, this is good enough. But if you need further simplification, you can write this one as you can say you can pull out x squared and an ex. So if you pull out x squared and an ex, you get here x plus 3. Okay, so this is very useful. And why we want to do that? Because especially in Calc 1, if you want to find the critical points, you have to do that because you need to completely factor. So in that problem, this is very useful. Okay, so useful for critical points. Okay, useful when finding critical points. Okay, so when you find critical points, this is useful because you need to completely factor. Okay, good. So let's do one more problem. So we can do like a little bit of extra problem because this is one of the major types. So d over dx. How about this one? 10e negative x fifth. Again, so how we do it? So we're going to do the second version of this, e to the fx version. So 10 is a constant. E, repeat the function, no change, and multiply by the derivative of the fx function. So we multiply by the derivative of the negative x of fifth. So let's do that. So it is 10 e negative x fifth. Derivative is simply negative 1/5. Now you can simplify this a little bit. We have 10 and 1/5, so it is negative 2, and then e to the negative x fifth. So that is the final answer for that. So let's do a few more. So let's do a problem with different variables. So let's do problem with theta. So d over d theta, e to the theta squared plus 1. So you can see here the function is inside function theta squared plus 1. So that means your derivative is going to be, when you have e, you just repeat the function. So it is e theta squared plus 1, no change, and then multiply by the derivative of the inside function. Okay, so that means e theta squared plus 1, the derivative of the inside function 2 theta. So what we normally do is we don't leave it like that. We're going to bring 2 theta in front, and we write this one as 2 theta e to the theta squared plus 1. So that is the final answer. And then let's do this problem. So let's say d by dx, e to the let's say square root x. So again, same argument. So when you have exponential function, we repeat the function, multiply by the derivative of the inside function. So in this case, square root x. So that means it is 1/2 x to the negative 1/2. And if you write this with the positive power, you can write this one as e to the square root x divided by 2 square root x. Okay, so it's very clear. How about this one? D over dt e to the tan t. So be careful when the variable is t because it's going to confuse with tan. Same argument, e to the tan t, and then multiply by the derivative of the tan t, which is secant squared t. So you can leave it like that. We really don't need the dot here, but that's just an exaggeration. Good. And how about this one? So just a little bit of complicated. E to the cosine theta squared. So you can see we have a e, and then we have cosine, and then we have squared function. Okay, so you have 3 functions here. So what we do every time, you multiply by the derivative of the inside function. Multiply by the derivative of the inside function. I'm going to do this step by step just to make it clear. So let's start the first function. What is the exponential function? So it is e cosine theta squared. And what we do now? we multiply by the derivative of the inside function. In this case, the inside function is this. So we multiply by the derivative of that. So that means cosine theta squared, the derivative. So that's the first one once you use the chain rule. So now let's try to do find derivative of that. So that means the next step would be e cosine theta squared. So let's try to find the derivative of the inside function. It's a cosine function. That means it is negative sine theta squared, no change, and then again multiply by the derivative of the inside function. In this case, the inside function is theta squared. See, you every time you multiply by the derivative of the inside function. Okay, so you can see in this case the inside. So first the function was cosine theta squared, and then we can jump to the next one. So then here the inside function is that. Okay, so that's what you get. Now what we can do, we can multiply by that. That's easy to find the derivative of that. So that means you're gonna get e cosine theta squared. We have a negative sine squared theta squared, and here we get 2 theta. So finally we can write this in a proper way. What we normally do is we write the negative sign first and the numbers, and then we write theta. When we have exponential function, we normally write the exponential function next, and then the other trig functions. Okay, this is kind of a customary way to do it. Okay, so that's the final answer for oh no, that's my square here. I think I made a mistake here. I had extra square, so there's no square here. Okay, let's write that part again. Yeah, so I just added a square there. So that's the final answer for this problem. Okay, so you can see, so what we did, every time you multiply by the derivative of the inside function. Okay, so you can see, so this is the first one that we get, and then so we take the derivative of the cosine theta squared, and then you take the derivative of the theta squared. That's it. Okay, there are two inside functions, cosine and theta squared. So that's it. Okay, so and then after that we write the solution like that. So that's the kind of idea. Okay, let's do just practice this more. I'm going to do 2 more problems just to tell you like how it works. So every time multiply by the derivative of the inside function. That's what you need to remember. So let's have d over dx x cubed e x squared. Okay, so so what's going to happen now is, so you can see we had is first we had to use the product rule. So according to the product rule, you write the first function as it is, take the derivative of the second function, and write the second function as it is, take the derivative of the first function. So again, what's the formula? uv prime vu prime. Okay, good. So then we have x3. If you take the derivative, it is e x squared multiplied by the derivative of the inside function, which is 2x, plus e x squared, derivative is 3x squared. Okay, so let's see whether we can simplify this a little bit. So if you simplify, we get 2e x squared x fourth plus 3 e x squared x squared. So we can leave it like that, or we can write the factored form, or either this is good enough. But if you need the factored form, you can see what are the factors you can get. You can get e x squared is a factor, x squared is a factor. From the first term you get 2x squared, from the other term you get 3. So those are the factors you get. Okay, that's a complete factorized version of that. And then you can see that this function is completely positive or 0. Okay, so you can see this is greater than or equal to 0. That means if x not equal to 0, it is increasing function. Okay, so only increases because derivatives has to be positive. But those are like other things that you use in Calc 1. Now so let's do maybe two more examples. So how about this one using the other formula? So the derivative of 5 3x plus 1. According to the third formula, you can see when you have other bases, we do the same thing. So the 5 3x plus 1, you repeat, multiply by the derivative of the inside function, which is 3, and then you have extra term ln 5, okay, to the ln of the base. And then, I mean, there are no much better ways to write this one. You can probably write 3 in front, and then we have times 5 3x plus 1 ln 5. Okay, maybe this one. Good. And how about this one? So d by dx 2 to the x squared. Very similar problem. So it's 2x squared. Take the derivative of the inside function, which is 2x times ln 2. You can simplify this a little bit. So what we can do is we can combine the 2's. So that means the 2x squared plus 1, because you get one more, and then we have x and ln 2. So that's the final answer for that. So as the one last problem, let's try to do this one. So this is d by dx. Let's say 1/4 x e to the 4x minus 1/16 e to the 4x. So do the first one, we can use the product rule. So you're gonna get 1/4. If you use the product rule for the first one, so it is you write the you take the derivative of the first one, rewrite the second one as it is, plus write the first one as it is, take the second one, which is 4e4x. Now it is clear, I think. Okay, and then minus 1/16, take the derivative, which is 4 times e to the 4x. So you can see there are some simplification here. For example, if you simplify, this is 1/4 e to the 4x. That's exactly the same as the first term, so that means you can cancel these two terms, so it's going to go away. And then after that, you can see you can cancel 4 with 4, so your final answer simply going to be x e to the 4x. Okay, so that means according to the antiderivative results, if you integrate x e to the 4x, you should get the long expression. Okay, so we're gonna learn that later, how to actually do that. Okay, so if you integrate this one, you should get the long one. This is one of the examples we can do later. So we're gonna use a technique called integration by parts. Integration by parts. So that's we learn in Calc 2. Okay, so yeah. Okay, so that's about that. Next, we're gonna learn about logarithmic functions. So how about this problem? With 5 functions. So let's say cosine. Um, um, just put some numbers. Okay, so cosine. Let's say cube. Inside you have 10, and then you have exponential function, and inside you have secant square root x. So you can see how many functions we have. We have cube, and the cosine, tangent, exponential, secant, square. So you have 6 functions there. So every time, what are you going to do? Multiply by the derivative of the inside function. So the first function, let's try to identify the first function. So this is like cosine some function to the cube. Okay, so that's how it looks like. So you have a cube, and then you have a cosine, not cosine x, cosine some function. Okay, like that. So that means we can use the general power rule for this problem. We can use the general power rule. So if you use the general power rule, the first term going to be, so this can be lengthy. Okay, so it is because it's like a function to a power. So that means 3 cosine gonna be 2 now because you subtract 1 and whatever inside. So we're gonna multiply by, we're gonna put whatever inside, no change. So tan e to the secant square root x. Okay, good. What's the next step? Multiply by the derivative of the inside function. So what's the inside function in this case? So next function is, because you're done with the power function, next function is the cosine function. So let's multiply the derivative of the cosine function. That's going to be negative sine whatever the rest. So we can repeat that. So tan e to the secant square root x. So we're done with the first inside function. Okay, good. The cosine. Now we go on to the next one. So what is the next inside function? So the next inside function is the tan part. So this is the next inside function. So we can multiply by the derivative of that. So let's do that. So times the whole thing. Okay. So derivative of tan. That means it is secant squared whatever the function. So it is e secant square root x. You don't need a parenthesis around because this function is clear this time. Again, now we multiply by the inside function again. If you want, you can add a parenthesis, that's okay, but you don't need that. Now, what's the next inside function? This is the next inside function. Multiply by the derivative of that. So times the derivative is, if it is exponential function, we know that you can repeat the function, no changes, and then again multiply by the derivative of the inside function. That's the inside function, secant. So multiply by that. So if you multiply by that, it's a secant. So that means secant tan. So you're going to get secant square root x tan square root x. We still have one more inside function. This is the next inside function. So we multiply by that. So if you multiply by that, you get 1/2 x to the negative 1/2. So that is the final. So what we can do is you can combine them in a nice way and write the final answer. So this still can be a little lengthy. So I'm going to start somewhere here because it's a long problem. So what we have, we can write numbers first. So I'm going to go negative. There's a negative sign, 3/2, and then we normally write the exponential function. Also, we can bring the negative half, that term down. So and with the exponential function first. So I'm going to write e secant square root x divided by square root x. So we have that, and then we can write the cosine squared term. So we have cosine squared tan e to the secant square root x, and then what we have is times the sine function. You can write next sine, again tan e secant square root x, and then we have secant squared. So you can write the secant squared now. So we have secant squared e secant square root x, and then we have the secant and tan terms. So we can write secant square root x tan square root x. So that's the final answer, but you can see it's lengthy, but you see what you did is every time you multiply by the derivative of the inside function, you jump one by one. Okay, just jump to the next one, jump to the next one. Okay, so if you think about this again, we start with the power function and then go to the so we can write the steps that we did. So we start with, yeah, so this can be useful. So we start with the cube function, then you went to the cosine function, then you went to the of the cosine, then you went to the tan function, after the tan, then you went to the so we take the derivative of tan, and then we have the exponential function, and then after the exponential function we went to the secant function, and then we went to the square root function. Yeah, So those are the steps that we went by. So start with the cube, I write the cosine, and then write the tangent, and then write the exponential, and then write the secant, and then square. So the best thing would be just try to rewrite it, just to rewrite it and see whether you can get, because if you can do this, you can do any problem. Okay, so it's very clear. Okay, let's do one last problem. But it's not lengthy, but it's like interesting problem. So the next one, we can do, let's say d over dt, e to the t tan t. Okay, so again, it's an exponential function. That means you repeat the function, no change, and then multiply by the derivative of the inside function. Good. So you have to use the product rule. So what is e t tan t? The derivative of this one is the derivative of the first term, rewrite the next one, and then write t, take the derivative of the second term, which is secant square t. Now what we do, we gonna rewrite them with some simplification. So we say e t tan t. Here it simply become tan t plus tan t plus t secant square t. T secant square t. So that's the final answer. Okay, so that's about that. So next, what we're gonna do, we're gonna go to the next important topic, the logarithmic functions. Okay, logarithmic functions. So let's go to that topic now. Logarithmic functions. Logarithmic functions. When you talk about in calculus, we can use the base e. So that's one of the result that we use. And but if you want to use other bases, you know that you can convert that because we have this result. What it says that log a to b x is simply equals to what we can do. We can just take the natural log of uh, uh, so let's like we don't need this right like that. So when you have something like log a to b, log base a to b, this is simply equals to you can pick any base you like. So for example, if you use natural log, so you can write this one as ln b over ln a. So that means using this result, you can always convert any base problem to natural log. So that means, but when you take the derivatives, you want to make sure that you always use a natural log. But if it is any other base, you can use this result to convert that into natural base. Okay, good. So now what we're gonna do? So let's go with the natural log problem, and also we also know some other facts about natural log and exponential function. So we can use those also to kind of simplify problems. Good. So so one other result that we know is we know that if we have log uh, a b equals c, which is equal to simply a to the c equal b. So we can write it like that always. Okay, the a is the base, c is the power, and b is the number. Okay, so you can always use the conversion. So what we know is we know two major results for derivatives of natural log functions. So it is d over dx. Ln, we use absolute values 1 of x. That's the first result. The other result is if you have ln some function, it is simply the function goes down, the derivative goes to the top. Okay, so those are the two major formulas for derivatives of log functions. So you can see we use a natural log, ln, base ln here. Okay, so let's try to do some problems from this. So we can have this one. This is the first problem. So let's say d by dx, x to the fifth power ln x. Again, you can use the product rule here. So one more thing, we need a parenthesis around because there are two functions, so you need the parenthesis. So, and then again, we're going to consider the u function. We're going to consider the u function and the v function. That's the u function and the v function. So let's use the result. We know the derivative result is, again, it is u v prime v u prime. Okay, u v prime v u prime, and with the plus sign. There's no order. You can write anything you like first. Good. So let's take the derivative of the first one, 5x to the fourth. Rewrite the next one plus rewrite the next the other one and take the derivative of the second one. So derivative of the second one is 1 over x. Okay. Now you can see there is a nice simplification here. You can see the first one is 5x fourth ln x, no change. But here you can see this can be simply x to the fourth power. So that we can leave as the final answer. Okay, there is a nice simplification like that when you have ln, because derivative of ln is 1 over x. Okay, so that's the first one. So let's do the second one. So how about this one, d over dx natural log 2x plus 1. Now we can use the second formula, according to the second formula. So this is the fx function. Okay, so that's the fx function. So that means you write the function down and the derivative on top. Okay, so that means simply going to be 2x plus 1. The derivative of 2x plus 1 is 2. So that's the answer for that. So 2 over 2x plus 1. Good. A little complicated one, d over dx. Let's say ln x to the fifth power minus x to the cube. Again, the function goes down, so the function is x to the fifth power minus x to the cube, and take the derivatives. The derivative of the first function is 5x to the fourth. Derivative of the second function is 3x squared. And now what's going to happen? You can cancel common terms. What's the common factor? You can see x squared is the common factor. So we're going to divide each term by x squared. So you finally end up getting 5x squared minus 3 over, if you divide by x squared, it is x3 minus 1. x3 minus x. Okay, because we divide by x squared. x3 minus x. So that is the final answer. Good. Now let's try to do an interesting problem using that has a trigonometric function. So what about this one? d by dx. This is a special problem. Okay, you can see this is a special problem. Natural log sin x. So this also works even if you don't have the absolute sign, but when you don't have the absolute sign, you have to be careful. That function has to be positive because this is natural log. It's a log function. Whatever you plug in has to be positive. Okay, the same argument. Function goes down. The derivative of the bottom function goes up. Derivative of sine is cosine. Now you can see cosine over sine means cotangent. So that's what you get. So you get cotangent when you take the derivative of ln sine. Okay. Similar one, d by dx. What about secant? Not the secant, sin x. Cosine x. Okay. Cosine x. If you do cosine x, it's similar. So cosine goes down. Our derivative of cosine means negative sine x. If you write the negative sign in front, this is negative tan x. Okay, so this is also we're gonna talk about these two later in Calc 2 class because you try to integrate these two functions. you try to integrate tangent and cotangent, and you can see you right now you know the answer, because if you know the derivative you automatically know the integral, because if the integral of cotangent should be ln sin x according to this result. Same argument. The integral of tangent has to be negative ln cosine x. The negative sign flip the term inside, so that means the integral of tangent has to be, according to this result, I'm going to write that. So what's going to happen, you can see this is a result already. The integral of tangent x has to be, according to this result, negative ln cosine x. So right, plus c. Now the negative sign flip the term inside, that means it's going to be ln secant x plus c. So we're going to see, we already proved the result, but this is a identity that we use in calculus. Okay, so integral of tangent x is natural log secant x. Okay, good. So so let's do a few more that involve those log functions. So there are really interesting results here. So how about this one? So the next one is let's say d over d theta natural log secant theta plus tangent theta. Really nice one. Okay, take the derivative of natural log secant theta plus tangent theta. But we know that when you have a function like that, the function goes down. So the function is secant theta plus tangent theta, and on the top the derivative of the on the bottom function, derivative of secant means secant tan, so secant theta tan theta. Derivative of tangent is secant squared theta. Okay, so what we use is we put the function on the down and the derivative on top. Okay, that's the idea. Okay, now let's simplify. You can see secant theta is common. So if you take secant theta out, you're gonna, as a factor, you're gonna get tan theta plus secant theta. In the bottom, it is secant theta plus tangent theta. So what happened now? You can see this term get cancelled. See, let's get cancelled. You simply end up getting secant theta. So that tells you a lot. That means we have a new formula. That means the integral of secant has to be ln secant theta plus tan theta. Okay, so this tells you that. So let's try it. So this tells you that the integral of secant theta d theta has to be ln secant theta plus tangent theta plus c. So that's the formula. Again, we do the same thing in our calculus 2 class. Okay, so but we prove that, so that's the result. Okay, so that's one result. Okay, let's do maybe one last problem before we move on to the other type. So d over dt, how about ln 4t squared minus 1, the, let's say some root like 4th root. Okay, something like that. So you can do this problem in a difficult way and easy way. Difficult way is just consider this whole thing like ln inside the function as the fx, but we are not going to do it. Okay, so the one way to do this is consider this function as fx and use the f prime x over fx formula. Instead, what we're going to do, we're going to simplify the log function, because this is much easier. So this one you can write as d over dt natural log, the function is 4t squared minus 1 1/4. We know that when you have a log, this 1/4 you can take it out. Okay, you can take it out. So that means you can rewrite this problem as 1/4, you take it out, d over dt natural log 4t squared minus 1. This is very easy to do. Okay, now we use a formula. So if you use a formula now, you will get 1/4, function goes down, 4t squared minus 1. The derivative goes to the top. The derivative of this function is 4 times 2t, right? 4 times 2t. So you can see 4 and 4 get cancelled. So you simply end up getting 2t, 2t over 4t squared minus 1. Okay, so that's the answer in a much easier way. But if you just use the whole function, that'd be complicated. So we don't do that. We normally simplify the natural log, because it's going to make the calculation easier. Good. So let's talk about what happens if you have a other base, like not this base but different base. So we have this formula. So we have d over dx log, let's say base a fx. So something like that with other base. So if you have other base, what's going to happen? It's going to be pretty much the same, but you need to divide by ln a. So what you do, so we have fx f prime x as before, but you divide by ln a. So that's the only difference now. Okay, so just divide by ln a if you have any other base. Good. So let's do just two problems from this one just to see. So we have d over dx. Let's say log 3 x squared plus 5. So if you have that, so it's going to be function goes down, x squared plus 5 divided by ln 3 in this case, and the derivative goes to the top. Derivative is simply 2x. You can see you can simplify, so we'll leave it like that. So let's do one more. What is the derivative of d over dx? Log cosecant x. So if you have log cosecant x, okay, when you write just log, what does that mean? When you write just log, we mean that the base is 10. Okay, so the base is 10. When you just write log, we assume that the base is 10. Okay, so the base 10, we normally don't write that, we just write log. So be careful with that. And also, but in computer science, when you write log, they mean the base 2. Okay, so let's write that. In CS, in computer science, log mean log 2, base 2. Okay, so you have to be careful with these special situations. Okay. Now, so what we have, so we use the same result. So we can write this one as the function goes down, ln 10 now, and then derivative secant. When you have cosecant, derivative is negative cosecant cotangent, so it's become negative. Cosecant x, negative cosecant x, and cotangent x, and you can see cosecant get cancelled, so you simply get so you simply get a negative cotangent x over ln 10, cotangent x, not cotangent t, cotangent x, sorry, cotangent x over ln 10. So that's what you get. Okay, so let's see a little bit of summary of what we did and what kind of formulas we have so far. So we need to, so let's talk about summary so far. Okay, so what we have is when you have, so we are trying to take derivatives. Okay, so so what's going to happen is, we know if you have xn, we know the formula, which is nx n minus 1. And then we have the general formula when you have fx to the n, it is simply n fx n minus 1 times f prime x. Okay, and then what we have is we have efx. So we have e to the fx, and we have actually ex first. We know ex. If we have e to the x, it is easy. Just go with the general case. So when you have e to the fx, that we can do, it is e to the fx, no change, multiplied by the derivative. And then we talk about a to the fx. A to the fx. So when you have a to the fx, a to the fx, so what's going to happen? A to the fx, f prime x, and then we multiply by ln a. So now the next situation is, what are you going to do if you need to take the derivative of a function to a function, like as a power, like that. So if you get a situation like that, so this can be complicated because we don't know what to do, because none of them are constant. In the first one, n was a constant. In the second one, this was a constant. Okay. Now, so that means you can do both cases. In the first one, n is a constant. So n is a constant. In the second one, a is a constant, or a or e. But now in this one, none of them are constant. Either power or the base, none of them are constant. Okay, so here the power is a constant. So this is power is a constant. Here the base is a constant. So now what we are going to talk about is, what if none of them are constant? So that means we don't know what this case. So that means we need a new result. So this is what we call the logarithmic differentiation. So let's talk about the logarithmic differentiation. You need that to do this problem. So logarithmic differentiation. Okay, so this is especially useful in two major cases. So we're gonna talk about one by one. Type 1 is, so let's say type 1. In the type 1, you're gonna see product or division of several functions. So when you have product or division of several functions, you're going to use the logarithmic differentiation. So let's do a problem. So let's say find y prime if y equal, let's say x to the 4th power x cube minus 2 square root, and then divided by x to the 5th power and then x to the 5th power x plus 1, maybe something like that. Okay, if you just have x to the 5th power plus x plus 1, you need to simplify that first. Okay, so let's say like you get something like that. You can see that it is not just one function, but there are more than two functions. If you have two functions, you can use the product rule, but since you have three functions, you cannot use the product rule. I mean, you can do for 2 first, and then you can do that product again, but that can be complicated. Okay, So what we can do, we can use this logarithmic differentiation for this problem. So what we can do, we take, so the steps are, if you want to do that kind of problem, so we can do take natural log, take what we normally call take ln of both sides first. Okay, that's what we do. So if you take the natural log of both sides, this is going to be ln y in this side. And what's going to happen on the other side is, as you can see, ln this expression, this whole expression. So we have x to the fourth, x3 minus 2 square root divided by x fifth plus x plus 1. Now what we can do, we know that when you have a sum, we know this result. We know that ln AB is equals to ln A plus ln B, and also when you have ln C over D, the division, which is equal to ln C minus ln D. So we can use that for this problem. That means using that, we can write this one as three natural log functions. We can write this one as ln x to the 4, the first function, plus ln x cube minus 2 square root minus ln x to the fifth plus x plus 1. Now what we can do, now we take the derivative. Once you take the derivative, you can take the derivative of those functions separately. Okay, so take the derivative. Okay. So we can take the derivative. So once you take the derivative, you can do that one by one. So actually, you can see before we take the derivative, what we're going to do is we're going to simplify this a little bit, because you can see that you can bring this 4 in front and here 1/2 power in front. So we do that first before we take the derivative. We discussed this before because it's going to make the problem simpler. So let's do that. But after that we can take the derivative. So we can write this one as first ln y, take the 4 in front, so 4 ln x, and then the next one you can take 1/2 ln x cube minus 2, and then we have minus ln, no change here, x to the fifth plus x plus 1. Good. Now we take the derivatives. Okay, so taking derivatives, okay, so taking derivative, we have to use a chain rule for this part, ln y. So you have a function, so what we can do, according to chain rule, it's going to be 1 over y and then multiply by dy over dx, okay, by the chain rule. And then on this side, this simply be 4 1 over x, and then here 1/2. This one function goes down, the derivative goes to the top. The same thing, function goes down, our derivative goes to the top. Good. If you can, go ahead and simplify. Otherwise, what will happen? This is that dy over dx. If you multiply both sides by y, if you multiply both sides by y, then this side gonna get cancelled. So the other side you get y, you're gonna multiply by y, and then you're gonna have here 4 over x. I mean, you cannot do much here. So we have 3/2 x squared over x3 minus 2, and here we have 5 x to the 4th plus 1 over x to the 5th plus x plus 1. Now what we can do, we can replace y by original function. We know what is y, that's the original function. So which is x to the 4th, x3 minus 2 square root divided by x to the 5th plus x plus 1, and then we're going to rewrite this 4 over x plus 3/2 x squared over x3 minus 2 minus x to the fifth plus x plus 1, 5x to the fourth plus 1. So that's what you get. Okay, that's the final answer. You can see that it's won't be like, you can't do much with that. So you can leave it like that. Good, so that's the derivative of the function using the logarithmic differentiation. So let's talk about the second type, the type 2. So in type 2, what we can do, so let's talk about this type 2, logarithmic differentiation type 2. So this one major thing is used to find the derivative of, use to find the derivative of something like this. Let's say y equal, actually let's start it here. Yeah, that's okay. Like you have a function to a function. So you have a function and then you have a power like gx. So like that. So if we have something like that, then we use the logarithmic differentiation. You have function to function. None of them are constant. Okay, that's the case that we couldn't do. So if this is the case, that's why, and then we do the take the natural log of both sides. Take natural log. Take natural log of both sides. And after we do that, it simply become the product. So we use the product rule. Okay, so then after that, okay, so natural log. Okay, ln. Okay, and then what we do is differentiate. So differentiate with respect to the variable with respect to x using product rule. And implicit differentiation. I mean, in this case, you can simply say the chain rule, using the chain rule. We can discuss the implicit differentiation next. Okay, chain rule. So we need the product rule and the chain rule. And then what we do is after that solve for dy by dx. Okay, so solve for dy by dx. That's the last step. Okay, so those are the major steps if you want to do a problem like that. So let's do a problem. So let's say find the derivative of y equal, let's do easiest one, x to the x. Okay, that's the easiest case that we can do. It can be x to the square root x, I mean all the same. So you see it's a function to function. Okay, none of them are constants. So so we're gonna follow these steps. What is the first step? So take the derivative. Okay, so we can take the derivative. So taking, that's the first step, taking ln natural log of both sides. So if you do that, then what's going to happen on this side is going to be ln y on this side. The other side, it is ln x to the x. What we do is we're going to bring this power out. Okay, so power out. So this is x ln x. Now you can see this is just a product. So we use the product rule. On that side, on the other side, you use the chain rule because it's a function of some, not x, okay, it's just y. So that means you have to use the chain rule for that. So let's do that. Now we take the derivative with respect to y. Okay, so taking derivative with respect to not yx, taking derivative with respect to x. So what we have is so d over dx ln y. Here we have d over dx x ln x. For this side, you have this chain rule. So if you use a chain rule, y goes down, the derivative goes to the top. That's a chain rule. And if it is not clear, we can write it like that. So the function is y, so 1 over y, and then multiply by the derivative of that, so we can write it like this. That's the same thing as y prime over y. Okay, on the other side, you have to use the product rule. So if the product rule is x, ln x derivative, plus ln x, x derivative. Okay, vu prime, uv prime. Okay, let's find them. So this x, ln x derivative is 1 of x, plus ln x, x derivative is 1. You can see this, you can simplify. Cancel this with 1. So you're going to get 1 plus ln x. So you get. Now what we can do, we're going to multiply both sides by y. So then you're going to get dy over dx. That's what you're looking for is simply y times 1 plus ln x. Now what we can do, we can replace by y. Y is x to the x. 1 plus ln x. Okay, so that's the final answer. You can see that it's not long. Okay, it's not long, but this is how we do it. So let's do another problem, just another one. That's it. So let's say again find the derivative of x sine x. Okay, something like that. Just pick two functions. It can be sine to cosine, x to square root x, anything you like. Just the same way. So what we do, you can just write the answer for this problem like that. Okay. So what we're gonna do is we can take that as y and then take the natural log. Also, there's another way to write it, because we know there's an identity when you have e to the ln x equal x. So we can use that fact as well. So that's like another way to kind of do these kind of problems rather than doing this way. Let's do both ways. Let's do this way, and then next let's do the other way. Okay. So what's the first method we do? We're gonna let y equal your function. Okay, that's the first step. If you get problem like that, you can write the answer directly. So we're gonna pick this one as y, and then what's gonna happen? Ln y gonna be ln x sine x. So you need the parenthesis. Sine x comes out, ln x. Now what we can do? Use the just take the derivative with respect to x. Okay, using chain rule and the product rule. Good. So you're going to differentiate with respect to x. So if you do that, this side is going to be y prime y always. The other side you have the product rule. Is it sine x? Derivative of ln x is 1 over x plus ln x. Derivative of sine x is cosine x. I mean, you can't do much here. So you just get y prime, which is y times sine x over x. Again, you can't do much. Ln x cosine x. Now we replace by y, which is x sine x times sine x over x plus ln x cosine x. I mean, you can do one thing here, because x is in the denominator. You can subtract 1 from the powers. You can, if you want, you can write like that. Otherwise, this is okay. But if you want, you can write this one as x sine x minus 1 times sine x. Okay. Because you divide means subtract 1 power plus ln x cosine x. Okay, so that's the answer. But both are okay, either this or that. It doesn't really matter. It's not much. Okay, so the other method. What's the other method? We can use this result. We know that if we have x, if we have e ln x, which is equal to x if x is positive. Okay, we assume that x is positive. And also we have ln ex. This is true for any x. Okay, for any x. For any x. That's only for positive x. Okay, so we can use one of those results now. So I'm going to use the first one. Okay, so if you use the first one, now this is for how you can write this in one line, like without this. So we have d by dx, x sin x. Now this function you can write using this argument. So it's e ln x sin x. See, you replace x by x sin x. Okay, that whole thing you replace by that. Now the same thing, we can simplify this a little. So this is e. Oh, actually I forgot the derivative. So let's try the derivative. So derivative of, you replace this one by e ln x sin x. Now we can simplify this a little as before. So this one you can write d over dx. E sin x comes in front, ln x. Now we use the derivative. So it's a e to a function. So that means e to a function means what? You write the e to the function and then take the derivative of the inside function. That means sin x ln x using the product rule as before. Sin x 1 over x plus ln x cosine x. Now you can see the first term here is simply, you can simplify this back and you can see this is exactly the same as x to the sin x. So that's what happened. Okay, so this is simply again the same thing. So this is the other way, okay, that we were talking about. So we can use this technique. Why this is again? Because you can rewrite back. So you can move this term back to where it was. Okay? And then we know that ELN get cancelled, like here. So you can cancel ELN x. X equal x. That's how you remember. ELN cancel. So, and using that argument, you can say this is simply equals to x sin x again. So that's how we do it without that approach. Okay, so you can use one of those log identities to do it in one line. Okay, good. So that's about it. So what we do next is we're going to talk about inverse trigonometric functions. So let's do inverse trigonometric functions. So inverse trigonometric functions. Inverse trigonometric functions. So what are the derivative of inverse trigonometric functions? So we can start with d over dx, sine inverse x. Sometimes we write arc sine x. I normally use sine inverse notation. So this is 1 over 1 minus x squared square root. Remember the format. And then we have d over dx cosine inverse x. So what's happening is similar to sine but have a negative sign. That's the only difference. So this is 1 minus x squared square root. And then we have tan inverse. So let's do d over dx tan inverse x or the arc tan x. So this is easy. It is 1 plus x 1 over 1 plus x squared, and you can see there are no square root sign. And then similarly you have d over dx cotangent inverse x. Same thing, just a negative sign in front. 1 plus x squared, no square root. And then we have secant x, secant inverse x. And there are two versions. So I'm going to use the most common version, which has a square absolute value, and then x squared minus 1 square root. So what is the relation you can see it's opposite. It's have x squared minus 1. The other one has 1 minus x squared, and we have absolute sign here because it has to be positive. If you just write x, it's not valid uh, for negative numbers. So you need absolute sign here. So be careful what version you have. Okay, some people write this without x, without absolute sign, and in some books they have with absolute sign. So depending on what domain, because we know that when you define the inverse functions, you can pick the domain you want. So so you can, depending on different domain you pick, either you have to include the absolute sign or you don't want to. Okay, so it depends. So okay, and then the last one is d over dx, cosecant inverse x. Again, only difference is a negative sign in front. The rest is exactly the same as the other one. Okay, so those are the cases, and you can see the first one valid only between 1 and -1. So we can see when the absolute less than 1. The bottom line is valid when the absolute value is greater than 1. So this is valid for any, okay, any x. So x is in between positive infinity and negative infinity, so any values. Okay, so x can be in between positive infinity and negative, that means any number. But first one is only for absolute x less than 1, the bottom one is absolutely greater than 1. Okay, good. So those are the formulas for inverse trigonometric functions. Okay, good. And always, try to remember the domain where it works, because when you try to think of application, you need to be very careful with that. And also the different version of the secant function, secant inverse, because some books don't use the absolute sign, so you have to be careful with that, because maybe you try to write it, but it doesn't work. Okay, let's do some examples. Let's start with this one. So let's say d over dx. What is sine inverse 2x? Okay, something like that. So we can use the chain rule. So according to the chain rule, what you can do, you simply treat 2x as u. So if you do that, this is simply going to be, if you consider this as u, it is simply going to be 1 over 1 minus u squared square root, and then multiply by u prime. Okay, that's what happened. So that means if you use that idea, so it is simply 1 over 1 minus 2x squared square root times the derivative of the u function, that is 2. So if you can simplify this a little bit, you can write 2 over 1 minus, you can write this one as 4x squared. So that is the derivative of that function, just using the chain rule. So here we use the chain rule. Okay, so chain rule is very important. Okay, let's do maybe 3 more examples. And then how about this? Let's say d over dx, tan inverse, or the arctan x over 3 are the same argument. So it is 1 over 1 plus whatever you have into x, so it's x over 3. So we have x over 3 squared, that's the formula says, and then multiply by the derivative of x over 3. So multiply by the derivative of this. Okay. So that's the chain rule. So let's simplify this a little bit. So you're going to get 1 over 1 plus, if you simplify this, is x squared over 9, and then this is 1/3. And then how to simplify this? First you can do is you can multiply the top and bottom by 9 here. So if you do that, you're going to get 9 over 9 plus x squared, and we have 1/3 there. Now we can simplify this 3 with that, and you get 3. So that means finally your answer is going to be 3 over 9 plus x squared. Good. And then How about this one? D over dx ck inverse x squared. Um, Again, we can use the formula, so it's 1 over uh, x squared absolute value, and then this is x squared minus 1 square root times the derivative of the inside function x squared this time, so which is 2x. Let's see that we can simplify. We can actually cancel one of the x's. So when you cancel one of the x's, so what's going to happen is, so you can see this has to carry the sign, okay, because x squared is absolutely is always, that's always positive, but we have that x there, so that means finally what's going to happen is, so because this has to carry the sign, so that means it's going to be 2 over absolute x. So yeah, because this is x squared is always positive, so you don't need the absolute sign, and then x, one of the x's get cancelled, so you get simply x and x to the 4th power, x to the 4th power minus 1 square, okay, without the absolute sign, because the sign has to be there because there's x that carries a sign, so this way you can make sure that it carries a sign. Okay, good. So it can be positive or negative. Good. So how about this last problem? So let's say d over dt tan inverse 2t plus 1 over 3. Same argument. So we're going to go with 1 over 1 plus 2t plus 1 over 3 squared times the derivative of 2t plus 1 over 3. So you can write this one as before. This is simply 1 plus 2t plus 1 squared over 9. Here it is going to be 2/3 simply. Now again we multiply by the 9 and expand. If you expand the bottom, you get 2t squared, no, 4t squared plus 4t, and then and we have that plus 1 and plus 9, so plus 10, and then we have 2 over 3 as well. Okay, so if you simplify this, one of the 3's get cancelled, one of the 2's get cancelled, so you're going to get 6 divided by, you can divide by 2, so you're going to get 2t squared. Yeah, actually, so it's not 6, it's 3 now, because you can cancel one of the 2, so it's 3 divided by 2t squared plus 2t plus 5. Okay, that's what you should get as the answer. Okay, good. And these are useful when you try to do the integral, because you can go backward. We can discuss these kind of problems later. So you need to do the completing square, and then you end up getting this answer. Okay, so then let's move on to the implicit differentiation. Now let's talk about the next major topic, what we call the implicit differentiation. So implicit differentiation. So this is useful when the function is given as an implicit function, because there are a lot of situations where you cannot solve for y as a function of x. So in that case, what's going to happen? You're going to see you're going to get an implicit function, and then you still need to find the derivative of the function. So what we need to do is we need to use the implicit differentiation. Okay, so and how we do it? So used when y is given as a implicit function, So we're going to do like a couple of examples so it will be clear as an implicit function. Good. And then also what the major tool is the chain rule. Okay, so use the chain rule. Use the chain rule to find the derivative. Okay, use the chain rule to find the derivative. With respect to one variable. Okay, derivative with respect to one variable. With respect to one variable. But normally we pick x. Okay, so normally we're gonna pick x for that. Okay, so let's just go to directly to some problems, and we can see it's not that difficult. So let's start with this one. So let's say find dy by dx. Find dy by dx if let's say you have x squared plus y squared equal 4, something like that. So you can see that y is not given as a function of x, but as an implicit function. Okay, so what we can do, we simply use the chain rule. Okay, so we're gonna do differentiate. So differentiate with respect to the x variable. So if you do that, so since this is the first example, I'm going to show you all the steps, but later you can see that you can skip some of the steps. So you take the derivative of both sides. So this is 4. So for the left side, you have to use the chain rule. So derivative of the first term is easy. It is simply 2x. Now, you take the derivative of y squared. You can see it is a function of y. So we can use the chain rule and we can rewrite this problem like that. So we can say by the chain rule, you can rewrite this one as d over dy is a function of y squared. Now we have dy over dx. Okay, so that's what's going to happen. This is coming from the chain rule. So we take the derivative with respect to y first and multiply by dy by dx. Always, if it is not a function of x, you always need to multiply by a term like that. Okay, so that's you always get a term like that depending on the independent variable. Good. And the other side is a constant, so it's 0. Good. So that's what we have. Now we can. So here we use the chain rule. Okay. So we use the chain rule. Good. Now we can simplify this term. Okay, actually take the derivative of that with respect to y is 2y. So let's write that. So I can write it here. So we're gonna get 2x plus derivative of y square with respect to y is 2y. Here we can write the prime notation just to make it easy. So y prime equals 0. When you write prime, please remember that it's dy over dx. Okay, or whatever the independent variable. Okay, now what else we can do? We can divide by 2 both sides. So then you simply get x plus y prime equals 0. So you can solve for y prime and then you get the solution we need. Okay, so so we have x. That doesn't look like x. So we have x plus y prime. And then what we do, we move x to the other side and divide by y. So you're going to get dy over dx, that means y prime, which is equal to negative. You move x to the other side, divide by y. Okay, so that is the solution. So that is the what we call the slope of the tangent line, or the derivative of the function. And you can see that in the solution you also have y. So that's the difference. So this is different from what you did so far. So in the solution you may see y in there. Okay, now if you know the point, just plug in the point and then you can find the slope of the tangent line. Actually we can do that part. Let's add that part to the problem. So and then we assume that here y not equal to 0 because you are dividing. So if y is 0, what you need to do, you need to look at the limit. So what you do in that case, you can consider the limit from the left and right to y and see what's going to happen. Okay, So let's add this extra part to this problem. So let's say, find the slope of the tangent line. Find the slope of the tangent line. Okay, let's say just tangent. Okay, find the slope of the tangent to the curve. Exact same one. Okay, x squared plus y squared equal 4 at the point. So if you ask this kind of question at the point, let's pick any point in the curve. So for example, -1 square root 3 is in the point in this curve, because if you plug in that point, you're gonna satisfy the equation. Okay, at the point. So let's try to do that. So if you get a problem like that, so what they're asking is the slope of the tangent line. Slope of the tangent line is the derivative. Okay, slope is the derivative. We already have that there. But if you get a problem like that, you need to do that part first. Since we have that, what you need to do is just evaluate. Okay, so that means the slope. So slope of the tangent. Slope of the tangent is simply you evaluate the derivative. That means we use the notation. We write a bar and then plug in the point. That means evaluate at the point. That's what it means. Okay. So we evaluate the slope at the point, but we only know the slope. So it is x over y. You can evaluate at this point -1 square root 3. So that means you simply plug in the x value. So that's the x value. That's the y value. So let's plug in that. So that means the negative. X is -1. Y is square root 3. If you simplify, you get 1 over square root 3. I mean, you can rationalize. You really don't have to do that. So you can leave 1 over square root 3. Okay. Good. So that's the slope. Now we know the slope. We know the point. So we can find the equation of tangent line using the point slope point form. Okay. So the equation of the tangent line, the equations. These are the steps. So we did that. That's the next one. So the equation of the tangent. Equation of the tangent is y minus the y naught equal y minus y naught equal slope time x minus x naught. This is what we call the slope point form. So let's plug in y minus y naught, which is square root 3, equal slope is 1 over square root 3, and then x minus -1. So that means x plus 1. Okay, so you can simplify this just a little bit. So you can move square root to the other side. This is totally fine, but we can also simplify this. So if you simplify, what's gonna happen? Y equal, you have 1 over square root 3x, and then here we have 1 over square root 3, and then we have plus square root 3. So if you take the common denominator, what's gonna happen is you get 4 over square root 3. See whether you can simplify that. So that is the equation of the tangent line. So if you look at the geometry part, what's going to happen here? So let's just try to draw this. So this is a circle we are talking about. So the circle is with radius 2. So that's the circle we have here. So and then the values are -2, 2, 2, -2. So the point we are talking about is -1 square root 3. That means it's exactly half in between. So that's the point. So that's where you have, so it's a -1 and square root 3. So that is the tangent line you are talking about. So let's draw the tangent line. So if you draw the tangent line, you see that's the tangent line you are talking about. So what this says that the equation of this tangent line is simply y equal 1 over square root 3x plus 4 over square root 3. Okay, so it's very clear, and then you can see that how we use the implicit differentiation to find a find equation of tangent line using the what we call the implicit differentiation. Okay, good. So that's about that. So let's try to do a few more examples just to see, just to consider different cases. So how about this one? So the next one, find y prime if we have x3 plus y3 plus xy equals 0. So differentiating with respect to x, so we're going to differentiate with respect to x. It doesn't matter x, or you can even do y, but you need extra step if you do that. So we're going to differentiate with respect to x. So if you do that, what's going to happen? So this is the idea. Whenever you take the derivative uh, of a function other than x, remember to multiply by y prime. So that's how you remember that. So we have from the first term 3x squared, and then from the second term you can see that it is a y term. So what we can do, we can take the derivative with respect to y. So we have to use chain rule. So according to chain rule, we take the derivative with respect to y. So that means it's 3y squared and then multiply by y prime. So that's what you want to remember. You always multiply by the y prime when you have a y function. Okay. Now for the next one, you can see it's xy, which is a product. So you have to use a product rule. So when you use a product rule, it is you remember the product rule. It is u prime vu prime. Okay, with a plus sign. And then so that means vu prime. That means x. And then take the derivative of y, which is 1, and then y prime. Okay, plus and then y derivative of x is 1. On the other side is 0. So that's what happened. Now the next step is you're going to collect the y prime terms to one side and the terms without y prime to the other side. So let's do that. So that means you can have on this side y prime times, you can see 3y squared from this term, and then you also have y prime term there. So that means it is plus x. So those are the only terms with the y prime. Then move the other terms to the other side. That means negative. We have 3x squared minus y. So we're going to move the terms without y prime to the other side. Now what we need to do is simply you're going to divide the two. So that means you're going to get y prime equal, we write the negative sign in front normally. So it's 3x squared plus y divided by 3y squared plus x. So that is the derivative of this function. Okay, so let's go to another one. How about this one? So let's say find dy by dx if tan xy equal 1. Okay, let's say equal x. So let's put something interesting. Let's equal x. Okay. So what happened? Same argument. We're gonna differentiate with respect to x. With respect to x. So if you do that, again the chain rule. So we're gonna take the derivative of this one. So what you do, you just it's a tan. So that means it's gonna be secant squared xy, no changes, and then multiply by the derivative of the inside function. That step comes, and then on the other side is 1. Now so we leave it. So you can see that it's never change inside, and then for this we have to use the chain rule. We already did that before. So that means takes the derivative of the so we write x, and then y derivative of that is y prime plus y derivative of x is 1. So that's what you get, and 1. Now what we can do is as before, leave the terms with y prime on one side. So I'm going to do it here. Okay, so leave the terms with y prime on one side. So that means we have y prime x secant squared xy on this side, and then I'm going to move the term without y prime to the other side. So that means y secant squared xy. Now what we can do, we can divide. So that means y prime equal 1 minus y secant squared xy divided by x secant squared xy. So that is the answer for this problem. So let's do a complete problem now. So let's say find the equation of the tangent line, find the equation of the tangent line of the tangent to the curve so let's say x3 plus let's say to the curve given by, you can say to the curve this, okay, to the curve given by, it's not a curve, given by x3 minus 2xy squared plus sin y equal 8, okay, sin y equal 8 at the point let's say 2 0, and you can see that this point is in the curve, because if you plug in 2 to the x and 0 to the y, it satisfies. That means this 2 0 is one of the point in the curve. So the argument is exactly the same. We just take the implicit differentiation to find the slope and then plug in the value and find the equation. So let's do that as a complete problem. So the answer, taking derivative with respect to x, okay, taking derivative with respect to x. In the first term you get 3x squared minus, so you had to use the product rule. So we have 2x, take the derivative of y, that means so you're going to get 2y y prime plus, now you write y squared, take the derivative of the first one, so that means you're going to get y squared negative 2, okay, from the second term. And then we have sine is a sine y, so that means it's going to be cosine y y prime. Whenever you have a y, whenever you take a derivative of a y term, multiply by y prime. That's the only thing you need to remember. Okay, that's it. Whenever you take a derivative of a y term, multiply by the derivative of that. Okay, anything other than x, multiply by the derivative of that term, and then equal on the other side 0. So we get now the same argument. Collect the terms with y prime. So you can see y prime in two terms. I'm going to collect them. So we have y prime times, let's start the positive terms first. So we have cosine y, that's a positive term, minus we have 4 xy, okay, from those two terms with a prime. And then I'm going to move the other terms to the other side. So if you do that, you're going to get 2y squared and then minus 3x squared. So that's what you get. And again, we can divide. So y prime is simply 2y squared minus 3x squared divided by cosine y minus 4xy. So that's what you get. So that's a slope. Okay, that's a slope. It's a derivative, or this is the slope at any point. So what you need to do is we need to plug in the xy value to find the slope at that point. So you can see the slope at the point 2 0 is simply y prime evaluated at 2 0. That's a notation for that. So wherever you see x, plug in 2. Wherever you see y, plug in 0. That's what's going to happen. So let's do that. So that means it's going to be 0 because y is 0 and 3x is 2 squared over cosine 0 minus, it's y 0, so this whole thing is 0, so you don't want to substitute for rest. It's simply 0. Good. Now let's simplify this. We know that the cosine 0 is 1, so you simply get negative 12 as the slope. Okay, now we can write the equation of the tangent line. So to do that, what we can do is, okay, we can do that here. So the equation of the tangent line is, so let's say equation of the tangent. So it is simply y minus y naught, the slope x minus x naught. So it is y minus 0, that's the y value, slope is negative 12, x minus 2, that's x value. So it is y equal negative 12x plus 24. So that is the equation of the tangent line to the curve at the point 2, 0. Okay, that's a complete problem. Okay, so let's do another interesting problem. How about one with the natural log? Let's do this one. Find y prime if y equal natural log x squared plus y squared. So the same thing, y is in and out. So we can use the implicit differentiation for this one. Okay, so taking derivatives, derivative with respect to x. So we have this chain rule. So it is y. When you have y, so 1 times y prime. So we just simply y prime. So it is simply y prime by the chain rule. So this is log. So that means the function goes down and multiply by the derivative of the function, inside function. In this case, inside function is x squared plus y squared. Good. So let's finish it. So it is 1 over x squared plus y squared. Now this one x squared means 2x. This is y squared, that means 2y y prime. Okay, always you get the y prime if you know the x term. Multiply by the derivative of the inside function. And then the way we did before, so no changes. So you can multiply through and bring all the y terms to y prime terms to one side. So that means we can write this one as y prime, and we can see there's a y prime term on the other side. You can bring it here. So you're gonna get 2y over x squared y prime, and then we have 2x divided by x squared y squared. Certificate. Okay, so now isolate the y prime term. So it's y prime. So this is okay. Let's take the comma. So what do you get? 1 minus 2y x squared y squared. On the other side we have 2x x squared y squared, and then we can take the common denominator. Once you take the common denominator, you're gonna get x squared y squared minus 2y over x squared y squared. On the other side we have 2x x squared y squared, and then what we can do is we can simply divide. So you can see this is a common term, so you can cancel that. If you multiply the two sides by x squared plus x, that's going to get cancelled. So that means finally you're going to get the derivative as 2x divided by x squared y squared minus 2y. So that is the derivative of this function. Okay, it's not that difficult. Let's have a small note and see what's normally going on in a general situation, like a not general situation, but like a obvious situation with a different discussion. So let's have a small note. So I'm gonna say, so this is just for anyone who think like, in a different way. So let's say find the derivative dy by dx if, like obvious one, x plus y equal 3. We know that this is just a line. X plus y equal 3 is a line. So that means we can write this one as y equal negative x plus 3. So that means the slope is that. So that means what we get. This says that dy by dx, the slope is negative 1. So let's see how we get that using the implicit differentiation. Let's say we can use the implicit differentiation, okay, by mistake. You don't need that, okay. We can so differentiate with respect to x. So if you differentiate with respect to x, you get 1 plus this is a y. Y means what do you do? It's not an x term, it's a y term. So if you write the complete argument, what normally going to happen is you take the derivative with respect to y and then dy by dx. That's what normally we write on 0 on the other side. So this means that 1 plus derivative of y with respect to y is 1. So you get 1 dy by dx equals 0, and you can see clearly when you solve for dy by dx, you get negative 1. So that's exactly the same thing. So that means even in this case, it work. It should work, okay? But I'm telling, so this is like a, you don't need that, but if you did that by mistake, you still get the same answer, okay? So those two are the same. Good. So that's about that. So what we're gonna do next is let's try to do a problem. Let's try to find the higher derivative. Okay, let's just do one example using higher derivative. So how about higher derivatives? Higher derivatives. So we just do the same thing. Take the derivative again. So what we do, use the chain rule. Okay, use the chain rule and possibly product rule or quotient rules. And mostly the quotient rule, because you're going to get, once you take the derivative, you get the quotient. So, and the quotient rule. Okay, quotient rule. So we remember the quotient rule. So what's the quotient rule? When you take the derivative of u over v, it is v comes first, vu prime minus, there's a minus sign, uv prime over v squared. So that's the one. So we can use that. Okay. So let's try to, so we use the chain rule and the quotient rule in these cases. So let's try to do this problem. So let's say the problem is find y double prime if let's say x squared plus y squared square root equals something. Let's say 5, something like that. So if you get a problem like that, you can definitely use the chain rule, like just treating like that. Because you because square root function, and then we know what's the derivative of square root function times the derivative of the inside function. So we can do that. Also, another way to do this problem is you can square both sides, but be careful when you square. What's going to happen? It may introduce additional solutions. So be very careful when you square something, because it's not always the case. Okay, for example, if you have x equal 2, if you square it, x squared equal 4, but if you look at the solution for x squared equal 4, now you have x equal plus or minus 2. So minus 2 never was a solution. So that means if you say x equal plus or minus 2 now, that's wrong, because that's not a solution. So you have to be careful when you square. Okay, good. So what we can do is, so let's square it just to make the calculation easier, but be careful because it can introduce new solutions. Okay, so let's say first squaring. So that's the first step. First squaring, we have x squared plus y squared equal 25. Now what we do, we can use the implicit differentiation. Okay, then by chain rule for the implicit differentiation, we have 2x plus y squared, that means 2y, y prime equal 25 on the other side, that means 0. Now again 2 get cancelled, so you can solve for a y prime. So y prime is negative x over y. So that's what you get as the first derivative. Now what you can do to find the second derivative, you take the derivative again. Okay, so the using the quotient rule. Okay, so you can say using the quotient rule, we have y double prime, which is d by dx y prime, So that means you can take d by dx, the negative x over y. Okay, so just use the regular quotient rule whenever you take the derivative of anything other than x multiplied by the derivative of that function. Okay, so that's the argument. So that means this is that y double prime equal, so we can write here. So we can use the quotient rule, which is v u prime u v prime over v squared. So if you plug into that v, so you can pull the negative sign out, or you can just go with negative x as one term. Okay, so you can go with negative x as one term, or just pull the negative sign out. So it's up to you. So if you go like that, then it is v means y, and then take the derivative of negative x minus negative x, the derivative of y. So derivative of y means y prime, or you can write 1 y prime, okay, if you want like that, just y prime, and then y squared. So take the derivatives now. Negative x derivative means negative 1, so it's y negative 1, negative negative positive, so it is x y prime. So what you can do is you can substitute for y prime actually. So you're gonna get that y squared. Okay, so I'm gonna write the rest here. So this is equal. So what we have is negative y plus x y prime. We can substitute for y prime now because we know y prime equals negative x over y according to this. Okay, and then over y squared. So what we need to do is now is just simplify this. So how to simplify? You can multiply the top and bottom by y. So if you multiply top and bottom by y, you're gonna get negative y squared minus x squared over y3. And if you pull the negative sign out, this is simply x squared plus y squared over y cube. And you see that you cannot simplify this further. So that's the final answer. So that is the second derivative of this function. Okay, so you basically use the quotient rule for these kind of problems, because mostly what happens when you take the derivative, the first derivative, you get a quotient most of the time. So you have to use the quotient rule in that case. So when you use the quotient rule, be careful when you take a derivative anything other than x, you have to multiply by the derivative of that function. So that's exactly what happened here. Okay, because you try to take the derivative of y term, so you multiply by that. So this is simply 1 times y prime, but we normally don't write y, so 1 times y prime. Good. So that's about the implicit differentiation. Okay, so that topic is over. So next, what we're gonna do is we're gonna go into hyperbolic trigonometric functions. Hyperbolic trigonometric functions, because there are a lot of applications from that in calculus and other topics like differential equation, engineering. So let's talk about that. Okay, that's a new topic. So hyperbolic trig functions. Hyperbolic trigonometric functions. So let's write the definition of them if you are not familiar with that. So we define the hyperbolic sign. So it is like shin. That's how we call it. So you put an extra h there to mean the hyperbolic. Okay. So this is hyperbolic sign. So we write like that. So that is you add the extra h to mean that. So it's simply defined using the exponential functions. So hyperbolic sign is ex minus e minus x over 2. That's the hyperbolic sign. And the hyperbolic cosine. So hyperbolic cosine we say cos. So that is with the plus sign, ex plus e minus x over 2. And then we have hyperbolic tan. So we call it tan h. It is simply the division of hyperbolic sine over hyperbolic cosine as before. But once you do that, what will happen? 2 get cancelled. You simply end up getting ex minus e minus x over ex plus e minus x. So you can write this in several different ways. For example, you can multiply the top and bottom by ex. So then you get e to the, so you can write this one as e to the 2x minus 1 over e to the 2x plus 1. So there are a lot of different ways to write it. So this is just one way. Okay. Because that will be useful when you take the derivative, because you only have like a non-constant term, only two non-constant, because that's one is -1 plus 1. Those are like constants, so take the derivative is 0. So it's easier than the other one. Okay, so that's about that. So let's look at the graph of what the graph looks like. So I'm just simply graph them. So the first one, you can think of exponential function. So the so that means the graph of sin looks like exponential on this side, it goes through 0, and exponential on that side. So that's it, how it looks like. Those are exponential functions, because you can subtract the two functions ex and e minus x. Okay, good. And then if you look at the cosh function, so it's gonna be it's interesting actually. What I'm gonna do, let's draw it like that. It's gonna go through 1, because it's a ex plus e minus x. So that means it's going to go like this, exponential function, and then go to 1, and then again grow like that. And then you can see those are passed through 1. Okay? So you simply add the two exponential functions here. So here what you did was you subtract the two exponential functions. Like that, you subtract, and here you add them. So you have one like that, and then you have the other one like this. So this will go through half, so like that. You add them, and then we have the other one, the tan. So that's also very interesting. It's gonna stay between two asymptotes, 1 and -1. So the graph gonna look like this. So it's gonna go through this and go through 0 and go like that. So this is 1 and -1. So that's the graph of tan. So this is y equal sin x, sin x. This is y equal cos x. I delete the whole equation. Okay, so y equal cos x. This is y equal tan x. Good. Those are all hyperbolic trigonometric functions. And then you can see that some other things. This is a odd function, and then you can see that this is a even function, and this is also an odd function. Okay, so odd, even, odd. That's what we expect. So you can see there are some features that belongs to the trigonometric function. That's one of the reasons why we call these hyperbolic trig functions. Okay, trigonometric functions. And then so let's try to do one thing. If you take the derivative of the first one, so let's just do one to show you what's going on here. So hyperbolic sine, that means the derivative of ex minus e minus x over 2, and then you can see once you take the derivative, 1/2 you can write outside. If you take the derivative of the first one, ex, that means ex again, and then if you take the derivative of the second one, it is e to the so we have minus e minus x times -1, because if you take the derivative of the top, it's -1. Now you can see negative negative positive, so this is simply 1/2 ex plus e minus x. What is this? It simply become cos. Okay, so if you take the derivative of hyperbolic sine, you get hyperbolic cosine. Okay, And then this is the rest of the table. So we can add all six. So these are all the identities. So we have d by dx, shin x, which is equal to cos x. And if you do d by dx cos x, we expect a negative sign, but it's not. So it is positive here. So this is different from the other trig identities. Okay, it's positive, both positive. And then we have tan. So d by dx tan x. Okay, I'm gonna this a little closer. So d by dx tan x, which is following the same tradition. It is sec x, so we have a h with the h sign, and then we have d by dx cot x. So this is again very similar to the standard derivatives. So we have hyperbolic cosine x squared, okay, and then we have d by dx hyperbolic secant. Okay, this is different. There's a negative sign for this. Okay, in the regular one there's no negative sign, but the rest is the same pattern. So hyperbolic secant, hyperbolic tan, and the same thing. So d by dx hyperbolic cosecant x. This is also follow the standard pattern. So cosecant x, cotangent, hyperbolic cotangent x. So only thing different is this and that. Okay, because they have, this one doesn't have a negative sign, this one have a negative sign. So that's the only differences. I exaggerate that. Okay, so those are the identities for hyperbolic trig functions. Okay, good. Next, what we're gonna do? We're gonna write the inverse derivative of inverse hyperbolic trig function as well. Okay, good. And then we have inverse hyperbolic trig functions. Okay, so inverse hyperbolic trigonometric functions. Hyperbolic trig functions, trigonometric functions. Good. So let's write the list. Again, we have identities for all six. So start with the first one. So it is d by dx hyperbolic sin inverse x. So which is 1 over 1 plus x squared. So you can see it is different from the regular one. There's a plus sign here. And then the d by dx cos hyperbolic sine, hyperbolic cosine inverse. So cos inverse x. So what's going to happen is 1 over x squared minus 1 square root. So you can see it's a different direction. Okay, so normally in the regular one we have 1 minus x squared, but this is different. So this is only valid for x positive, x greater than 1. And then we have d by dx tan inverse x. You can see it is also different. It is 1 minus x squared, 1 minus x squared. And this is valid only when x absolute x less than 1. And then we have d by dx cot inverse x. So which is 1 minus x squared. This is the same as a function, is the same, but this is only valid for absolute value x greater than 1. That's a less than 1, it's greater than 1. And then we have d by dx cosecant inverse x. So which is different is the minus. It's completely different from others. It has a x, and then 1 minus x squared square. You can see it's completely different. And this is only valid for x in between 0 and 1, this formula. And then we also have the last one, d by dx, cosecant inverse x, and this is again negative 1 over absolute value x. So you can see they are different. And then this side you have 1 plus x squared square root. Okay, and then this is only valid, it doesn't valid for 0, so x not equal to 0. Okay, good. So those are the inverse derivatives of inverse hyperbolic trig functions. Okay, so yeah, so this list. Good. So let's do like 2 or 3 examples just to make sure that we know how to do it. So I'm not going to do many, but now this is like completely, so we have everything we need to know. Good. So let's do like just a couple of examples, like maybe 2. So let's try this general case. So what if u is a function of x? So let's say there's a function u which is a function of x. So for example, we can write a general result for these inverse trigonometric inverse hyperbolic functions. For example, what is the derivative of uh, hyperbolic sine inverse u? So that means we can simply use the chain rule. So according to the chain rule, what you're gonna replace x by u. So that means it can be 1 over 1 plus u squared, because we normally have 1 over 1 plus x squared square root times the derivative of the u function. So that is the formula that we have. So this is simply coming from the chain rule. Okay, from the chain rule. And then you can see the similar results exist for others. Okay, similarly for others. Just to see this in action, let's do like 2 examples. So let's say find the derivative of let's do 2 problems. So let's do this one, d by dx cos square root x. And you can see there's only one function, you don't need the parentheses for this one. So by the chain rule, cos becomes sin, no negative sign, is positive, and then multiply by the derivative of the inside function. So this means it is sin x square root x. This is 1/2 x to the negative 1/2. If you rewrite with the positive index, so this is sin square root x over 2 square root x. So that's what happened. And then for this one, this is d by d theta. We have tan inverse sine theta. So let's see how this works. So we can use the chain rule argument that we just discussed. Tan. So tan inverse formula is 1 over 1 minus x squared. So according to that, it's going to be 1 over 1 minus x, now replaced by sine theta. So sine square theta times the derivative of the inside function. So that means sine theta derivative. So if you plug in that, so it's going to be 1 over, okay, 1 minus sine square theta means cosine square theta according to Pythagorean identity. Derivative of sine means cosine. Now what's going to happen, you can see one of the cosine get cancelled, so you get 1 over cosine theta. 1 over cosine theta means secant theta, so that means simplifies very well. Okay, so that's how you use the hyperbolic trig function and the inverse hyperbolic trigonometric functions. It's very simple. So let's do 2 advanced problems before we finish the section. So let's do a d by dx x tan inverse x plus ln 1 minus x squared square root. So so what we can do term by term here. So before we take the derivative, what we can do is we can rewrite this. So we can write this one as x tan inverse x plus, you can see this is a 1/2 power, so you can take it out and then we can write this one ln 1 minus x squared, because this is going to make it easy to take the derivative. Now once we take the derivative, you have to use the product rule here for the first one. So take the derivative of the first term, rewrite the second one, and then take the derivative of the second one and rewrite the first one. So we write the first one, take the derivative of the second one. So you can see that it is 1 over 1 minus x squared. So that's the derivative of tan inverse x. Plus we have here 1/2. The function goes down, the derivative goes to the top. So there are some simplification now. You can see these 2 and 2 get cancelled, and then what we have is tan inverse x plus x over 1 minus x squared, and here you have minus x over 1 minus x squared. So that means these two terms get cancelled. So the final answer is simply tan inverse x. Okay, so it simplifies very well. So that's the derivative of this. So that means if you integrate tan inverse x, this is what you get. And then let's do the last one of this section. How about this? d by dx sin inverse tan x squared. Tan x squared. So what we're going to do, we're going to use, we're going to apply the chain rule repeatedly. So we're going to start with the first one, sine inverse x. We know that the sine inverse x has the derivative, no, sin inverse x has a derivative 1 over 1 plus x squared square root. And because of that, the derivative of sin is 1 over 1 plus x squared square root. So because of that, your answer is going to be here by the chain rule 1 plus whatever inside you're going to put it here. So that means tan squared inside also have x squared and then square root times the derivative of the inside function, the derivative of tan x squared, that means tan, so that means the secant squared function is x squared, and also multiply by the derivative of the inside function, that means 2x, so derivative of 2x is derivative of x squared is 2x. So that's what you get. Now we can do we can simplify 1 plus tan squared theta because of the trigonometric identity. This is going to be secant squared because the square root. This is simply going to be secant x squared. That's what you get. And we also have secant squared x squared and then 2x. So you can see one of the secant you can cancel, so finally you end up getting 2x secant squared x squared. Good. So that is the derivative of that function. And also you can see that so this simply equals to so what other observations, because you have secant is squared, so actually that's not squared, so that was a mistake actually. So it's so it is simply because you could cancel one of them, so you could secant x squared, so that's what you get. Okay, there's no squared there, so that's the final answer. Good. So let's look at the one of the identity that's useful for solving inverse hyperbolic functions next. So we can see another identity. Another identity for we can see inverse hyperbolic functions. Okay, inverse hyperbolic functions. Hyperbolic trig function. So we have these identities that you can prove using quadratic formula. For example, you can show that sin inverse x, no derivatives, is simply equals to natural log x plus x squared plus 1 square root. This only valid, or this is actually valid for any x. And then we have cos inverse x. You can show that this equals to natural log x plus x squared minus 1 square root. And you can see that here this is x has to be greater than or equal to 1. And then we have similarly for tan inverse x. This is going to be 1/2 natural log 1 plus x over 1 minus x. Okay, so we have those three identities. Actually, this is valid for x, absolutely x less than 1. So these are some identities that are useful when you want to simplify certain functions. Okay, good. So that's basically the basic functions. The one last thing that we're going to do here is we're going to talk about the derivatives of parametric curves and polar coordinates. So let's talk about that now. So now let's talk about one of the interesting topic. So what we're going to do is what if you try to take the derivative of an integral. So we know that those two are inverse processes to each other. So that means we expect that if you do that, that means if you take the integral first and take the derivative, we expect that you get the function back because the two processes cancel each other. Actually, that's exactly what we get. That's what we call the fundamental theorem of calculus. So the fundamental theorem of calculus. So we call FTC. So let's talk about how it works. So I'm going to give this as a theorem. So let's try this as a theorem. So what it says that if the function f is continuous on an interval AB, then the function defined by the function g defined by gx, which is the integral from a to x. So a can be any number in that interval. It need not to be exactly the lower bound. Just pick any number in the interval. So integrate from a constant to x, the function ft, okay, dt. So and then this is so what happened here is, so a less than or equal x less than or equal b. So you pick a x in between that in that interval. So it can be a or b. Good. So what it says, if this is the case, so if f is continuous, that's the only condition we need. If it's continuous on the interval ab, then the function g defined by this integral is continuous. So let's try the shortcut. CTS, continuous on the same interval AB and differentiable. So that means you can take the derivative and differentiable on the open interval AB, not the closed interval, only on the open interval, okay, on AB. And the derivative of g is simply f, you replace t by x. So that's what it says. Okay, so that is, if you write this in another form, so that is, if you take the derivative of the integral a to x ft dt, which is simply equal to fx, you replace t by x. That is how we write the fundamental theorem of calculus. So it's like interesting result. This is very useful when you want to take the derivative of an integral. Okay, so only condition that you want to check is whether the function is continuous on that interval. Then you simply replace t by x, and also make sure that the format, it will be a to x. Okay, if it is not a to x, you have to bring it back to that form. So let's do a couple of examples. So let's start with the first one. So let's say write a problem, just one problem. Find the derivative of the following functions. Find the derivatives. Find the derivatives of the functions. Find the derivative of the functions. Let's start with the first one. Let's say gx, which is given by 0 to x, 1 plus t squared square root dt. So the worst thing to do is just take the integral first and then you take the derivative of that. We are not going to do that anymore. Okay, we don't need to do that because actually you don't know how to integrate this one. You need to wait until you learn some calc 2 stuff to do this. Okay, so but we can use the fundamental theorem now. So what do you know? So let's say so the answer. So since the inside function, I'm going to call it ft. In this case, it is 1 plus t squared. This is a nice continuous function on that interval. Okay, because 1 plus t squared is positive, so it's continuous very well. Okay, is continuous on the interval from 0 to infinity actually. So that means we can use the fundamental theorem of calculus. Okay, so then because of that, then we know that the g prime x is simply in this case fx. Okay, fx. So that means you replace t by x, that means 1 plus x squared square root. Done. Okay, so very simple. This is simply coming from the fundamental theorem, which says that it is just the fx function inside function. Okay, you replace t by x. Okay, that's the first problem. So let's do another one. How about this one? So let's say you have hx, which is, let's say, x to 1, 3t squared sine, let's say 4t dt, something like that. Okay, so what do you know about this inside function? That's the function you want to pay attention. So there are two things here. One is this in the right format? So you can see that it is not a constant to x, it is x to 1. So the first thing that we're gonna do is we're gonna switch that. We're gonna change the order. That means what we happen, you know that when you flip it, the negative sign comes out. So you can write negative 1 to x. So you're gonna do that. That's the first thing. And then we have 3t squared sine 4t dt. Now we want to check whether this function is continuous, and you know that these two, one is the first part is a polynomial, second one is a sine function. Both are nice continuous functions, so the product is also continuous. So yes, so this function is continuous. That means we can use the fundamental theorem. Okay, so it's continuous on the whole interval negative infinity to infinity. So that's very good function. Okay, so then according to fundamental theorem, what's going to happen is you can write h prime x, which is the negative. I can pull the negative one out. The d by dx, we can write 1 to x, 3t squared sine 4t dt, and then we know that that's in the right format now. So simply replace t by x. So that means the answer is negative 3x squared sine 4x. Okay, that's it. So what's the worst thing to do? Worst thing to do is integrate first. Okay, integrate and then take the derivative. But this is very quick. You don't want to do that. You just plug in, replace t by x. Okay, now let's try to do a slightly different problem. So number C. How about this one? Let's say you have function kx, which is 1 to x squared let's say cosine t dt or something like that. Okay, now what do you notice? You notice that this is not x anymore, this is x squared. Uh, and then you know that this is a cosine function, so this is continuous everywhere. So that's good at least. But the problem is this is not x anymore, it's x squared. So if you see something other than x, what are you gonna do? You're gonna use a substitution. Okay, so you're gonna say let u equal let's call let u equal x squared. Okay, so that's the starting point. Whatever the function you're gonna pick as u. Once you pick this one as u, you can rewrite this function using the new variable. Okay, so that's what we can do next. So after we do that, then you can say, okay, the kx function is now, it is 1 because you pick x squared as u, so it's going to be 1 to u cosine t dt. No change inside, you simply change. Now you can see this is exactly like x because x is just a variable. Okay, now we have a u. So that means we can use a fundamental theorem of calculus for this function now. Okay, but since it is go through the function u, we have to use the chain rule. So what we can do by the chain rule, you know the chain rule. So by the chain rule, what we can do, the derivative of this function is, what we can do, we're going to take the derivative with respect to u first and then du over dx. So this is coming from the chain rule. Now what we can do, we can replace them. So we can, what we can do is, this is d over du, we write that. So replace the function with the u new variable. So 1 to u, and then so we have cosine t dt. Okay, times, so I'm going to put a bracket here just to distinguish them, and then we have du over dx. Du over dx, we know what's the derivative of u function with respect to x, that is 2x. Okay, so that is the du over dx, that is du over dx. Good. Now for the first part, we use a fundamental theorem of calculus. So if you use a fundamental theorem here, you can see it is a 1 to u function. You take the derivative with respect to u. So they simply use a fundamental theorem of calculus. So what you're going to get is simply you replace t by u. So this simply becomes cosine u now times what we have from the other side. So that's the difference. So it's u. But you can leave it here like that because there's something you introduce. So you replace back u, because since we know that u equal x squared, so put that back in, and I also change the order, so I write 2x first to avoid confusion, so it's cosine x squared. So that's what happened. So you put the whatever the function inside and multiply by the derivative of that. So see what happened, you replace that by that function and multiply by the derivative. Okay, so that's how it works, and we can see that in this step we use the fundamental theorem of calculus. Okay, so we use the fundamental theorem of calculus to get the do the first part. Good, so that's how it works. So let's do one last problem um, to see more things, but otherwise just the same things. There's nothing new anymore. Okay, that's it. There are only two type of problems. So so how about the next one? So in this one, let's say you have a gx function, so which is so let's say 1 minus 2x cube negative 4 1 over 1 plus e to the negative t dt, something like that. Okay, what do you know about the inside function? There are a few things here. So the first thing is you need to switch the order, so we can do that. So we can read this negative and then negative 4 to 1 minus 2x cube 1 over 1 plus e to the negative t dt. That's the first thing, we switch the order. And then what do you know about this function? This is the exponential function, and we know that that function is the exponential part never gets 0. That means this is continuous everywhere. So continuous on negative infinity plus infinity. So that means everything looks good. So we can use the again the chain rule. So the first step is let u equal 1 minus 2x cube. That's the first step, and then we can use the chain rule as before. So what happen after you do that, then you can write your gx function in this form. So negative 4 to u 1 over 1 plus e to the negative t dt, and then you know that the negative is in the domain, so that means everything looks good. So now we can say by uh, the chain rule, and the fundamental theorem of calculus, we can write the g prime x, which is equals to the negative of the d by du, the integral from negative 4 to u 1 over 1 plus e to the negative t dt times du over dx. First part from the fundamental theorem of calculus is going to be 1 over 1 plus e to the minus u, replace t by u, times the derivative of u function with respect to x, and you can see that that is negative 6x squared. Okay, now the last thing we can do is we can multiply through first, negative become positive, and then replace u by the original function. So if you do that, you're going to get 6x squared over 1 plus e. You replace u by your function, so it's going to be 2x cubed minus 1. So that is the final answer for this problem. So this is how we use a fundamental theorem to find the derivative of an integral function. Okay, function given as an integral. Okay, that's good. So that's about the fundamental theorem of calculus. So that's the last topic. So derivatives of parametric functions. Okay, so derivatives of parametric functions. Derivatives of parametric functions. So there are something called parametric curves. So we learned this in Calc 2. So like for example, this curve. So let's say you have a curve like this, something like that. So the interesting part is when you have parametric curve, it can cross each other because that doesn't happen uh, in a regular function, because when you have function they don't cross each other, but when you have parametric curve they can cross each other. So that's one of the interesting ones. So that's the reason why they have a lot of applications. So let's say this is the starting value when the parameter equals to a, is the ending value when the parameter equals to b, something like that. Okay, so and then there's a direction, because where it's gonna move when the parameter increases. It's gonna go like that, go like this. So that's the kind of idea. Okay, and it's going to end up at this. Okay, these are what we call parametric curves. And when you have parametric curve, what we normally happen is you're going to give the x and y coordinate as a function of a parameter. So you can write this curve as x is a function of t is a parameter, and y coordinate is also a function of t. And then you can say t is in between the two values a and b, just to get the portion of the parameter. So this is how you write a parametric curve. Okay, so this is what is the parameterization of the curve. So all the familiar curves like straight lines, circles, ellipse, hyperbola, all of them have a parametric version of that you learn in Calc 2. So and then you can also see that you can solve, because you can remove this t from these two equations. Once you do that, what's going to happen? You get y as a function of x. Okay, so this happened removing the parameter. Okay, so removing the parameter, once you remove the parameter, removing t, in this case the parameter is t, you're going to get a function like that. So that means y is a function of x, so that means you can talk about those slopes and things like that. So so let's talk about that. So the slope at a point. Okay, so slope at a point. So let's say what we can do, we can differentiate this function with respect to t in this case, because t is a parameter. So differentiating with respect to t, what's going to happen? We're going to differentiate that. So we can write this one as dy over dt, but we know that the y is a function of x. So what we can do, we do dy over dx by the chain rule, and then rewrite dx over dt. Okay, so we introduce x in there. Now what we can do is we can solve for x. Okay, so if you solve for x, so what's going to happen? We can write this one as, if you solve for x, we can write this one as dy over dx, that's the slope, is simply dy over dt divided by dx over dt. So we can divide the two. So that's, so if dx over dt not equal to 0, so this is what we can use as the formula to find the slope. Okay, so take the derivative with respect to the t parameter of y divided by take the derivative with respect to t of x. So dy over dt divided by dx over dt. So that we can use as the formula. Now for higher derivatives, okay, so for higher derivatives, okay, so for higher derivatives, what we can do, we can write as the second derivative d squared y over dx squared. So what we do, we take the derivative of dy by dx. Okay, so that means we can use a simple trick here. So what we really need is, so we're going to take the derivative of, so you can use the previous formula. What we're going to do is simply replace y by dy by dx. Let's try and do so. You simply replace y by dy by dx to get this formula. So if you do that, then what's going to happen is this simply becomes d over dt of dy by dx divided by, in the bottom it is dx by dt, no change. So that means we get this formula simply using this formula. So you simply replace y by dy by dx. Okay, so that is the formula we use to find the higher derivatives. Okay, so we use this to find the second derivative. Okay, used to find higher derivatives, or in this case the second derivative. Okay, so let's do like 2 examples to see how it works. Okay, so let's do this as the first example. So again, so what we do is we use the exact same formula, so you simply replace y by dy by dx. Okay, that's the only thing we did. We replace y by dy by dx in the first formula. So that means you only need to remember one formula for both derivatives. Okay, so let's see this in action. So let's do this problem. So let's say find the first and the second. Find the first and the second derivative of find the first and second derivatives of the curve defined by the parametric equation equations x equal t squared, y equal t cube minus 3t. Okay, just 2 equations, it doesn't really matter, just put some equations there. So x is given as t squared, y is given as t cube minus 3t. So you can see that x is non-negative. Okay, so you see the graph only on the positive x side, so you can predict that there. Okay, so let's use the formula now. So according to the formula, we know that dy by dx is simply equals to dy over dt divided by dx over dt. That's what the formula says. So dy by dt, take the derivative of y with respect to t, so you're going to get 3t squared minus 3 dx over dt, that means 2t. So that's the answer. Okay. Also, you can write, you can divide by 2t top and top. So that means you can rewrite this one as 3 halves. If you divide by 2t, you're going to get t here minus 1 over t. Okay, so you can write like that. Sometimes this is useful, especially when you find a second derivative, because if you try to use the first one, it's a quotient, but now it's easy when you write it like that. Okay, so you're going to see the benefits. Sometimes we simplify like that. It's not a must, but they help you. Okay, let's look at the second derivative. So if you go for the second derivative, d squared y over d squared, according to the formula, what we're going to do, it is d over dt of dy over dx divided by dx over dt. So according to that, it is the derivative d over dt of the previous solution. We have this in this form because this is much easier to take the derivative. You don't need, you can avoid the quotient rule. Divided by 2t. And now we can take the derivative of the top. So it is simply 3 halves. You can take it out. If you take the derivative t means 1 minus, okay, 1 over t. If you take the derivative 1 over t, how to take it? T, you're going to bring it to the top. So t to the negative 1. So that means it's going to be positive 1 over t squared divided by 2t. Now what we can do is uh, this 2 and 2 become 4, so 3/4 t, and then you can multiply the top and bottom by t squared. If you multiply the top and bottom by t squared, you're going to get 3 t squared plus 1 over 4t cube. This is for t not equals 0. Okay, it's not valid for that. Okay, that's it. That's the second derivative. Okay, using a parameter. Okay. So this also tells you certain things. For example, it's concave up for positive t, concave down for negative t. Okay, and then also if you graph this one, you're gonna get a curve like this. So this is the parametric curve that you get for this. If you use the parameterization, if you plot certain points, so you're gonna get something like this. So you're gonna get like that, and go like that. Okay, so that's what you get. And you can see that at this point the slope is 0. Okay, so it's very clear. When you plug in t equal plus 1 or t equal minus 1, the slope becomes 0. That's exactly what happened at this point. Slope is 0. So this is for t equal minus 1, and this point slope is 0. That's for t equal 1. Okay, you can see that. And that's the point 3. Okay, so it's gonna move in like this. It's gonna go like that and go like this. Okay, so that's the parametric curve that you get for that. So let's just do one more example. So how about this one? So let's say find the slope. Find the slope of the tangent line, or let's say just tangent. We don't say line. Tangent is a line. Tangent to the cycloid, Okay, so there are certain special patterns. This is what we call cycloid. So cycloid is always given by like this: x equal r theta minus sine theta, y equal r 1 minus cosine theta, and then at the point theta equal pi over 3. Okay, at the point theta equal pi over 3. And then you can see that in this case the parameter is theta. So the parameter is theta. Parameter is theta. So let's try the formula. So according to the formula, it is dy by dx. And now the parameter is theta, so we can write this one as dy over d theta divided by dx over d theta. So that means y, you need to take the, and r is a constant, okay? R is a constant. Only theta is changing. So if you take the derivative with respect to derivative y with respect to theta, you're gonna get r is a constant 1, so 0 minus cosine, so which is minus sine theta. Same thing, r theta, so you get 1 minus cosine theta. And now you can see that r get cancelled. So you get sine theta divided by 1 minus cosine theta. So that's the slope. Okay. So that means at point, so at the point, theta, okay, let's say because it's not the whole point, so we can say when, let's say just when, because it's not the whole point. You can say at, simply say at theta equal pi over 3, so just find the pi over 3 value, so you're going to get the slope d over dx evaluated when theta equal pi over 3, so just find the pi over 3, so it is sine theta over 1 minus cosine theta evaluated at theta equal pi over 3. So that means just plug in pi. This is how you write the mathematics. Okay, so you need to understand how to write it. It's a language. So it is sine pi over 3 1 minus cosine pi over 3 sine pi over 3, which is square root 3 over 2. 1 minus cosine pi over 3 means 1/2. So that means if you simplify, you simply get square root 3. So that's the slope. Okay, that's the slope, and then you can, since you know the slope, and you can also plug in the value and find the x value and the y values, then you can get the point, and then you can use the slope point form for this one. Okay, so what is the shape of the cardioid? So what happened is, so if you graph this, so this, you get like a curve like this. So this is what we call the not the cardioid, the cycloid. So you're gonna get something like that. So like maybe like stretch circle. Okay, so that's what you get like something like that. Those are what we call the path of the cycloid. And at this place you can see the tangent line is like 90. Okay, so it's gonna go like that. Good. So we're gonna find the so you can find tangent at any point like that. So, okay, that's about that. And then the last thing we're gonna do is the derivative of what we call polar curves. That's just the extension of what we are doing right now. So let's do that as the last topic. So derivatives or the slopes in the other case. Derivatives or slopes of polar curves, polar coordinates. Okay, polar curves. So there's another coordinate system what we call polar coordinate. This have many applications. So in a polar coordinate system, what's going to happen? There's a line, and then what we can do, we're gonna start measuring the angle from the line. Okay, so we measure the angle from the line, and then you give a distance, how far you want to go. So that means you get the angle and then go a direction. So that's how it works. So let's say the angle is theta, so we use a regular sign convention of trigonometry. So that means if you go clockwise is positive, and if you go counterclockwise it's negative, so that's what we use, the same thing. And then this is the angle, so this is what we call the polar. So this starting point is called the polar. Okay, and then this line is what we call the initial axis. That's where I can start. And then you only need to give two information. You need to give what is the angle, and then how far you go, r distance. So r even can be negative. Negative means you go backward. Okay, so r positive means this, r negative means you go backward. Good. So you want to give the angle and the distance. Okay, so that's it. That's what we call polar coordinates. So we normally write the polar coordinates as r and theta. So r first and then theta. But when you actually do it, we do theta first. Okay, so r theta is how we write it. And then all polar coordinate you can write as r as a function of theta. That's how you write it, r as a function of theta. So that means it's just a regular another situation of the parametric curves. Here the r act as the parameter. Okay, so that means we can exactly use the same thing that we were discussing just a minute ago. Okay, so we can say a few things. Behaves as a parametric curve. Behaves as a parametric curve. Okay, behaves as a parametric curve. And then what we normally do is we can use a triangle to find the x coordinate and the y coordinate. So we can do that. So for example, if you drop a line perpendicular, so we're going to consider this as x and this as y. So you can give formulas for that. So you can see that x is simply r cosine theta, and you can see that y is simply r sine theta. Okay, that's what happened. So that's the coordinate, x and y coordinate. Now r is changing, theta is changing, both changing. Okay, r changes, theta changes. So you can see that both r and theta change. Okay, not just one, because theta is a function of r is a function of theta. Okay, so that means you can write this one as x, which is r is a function of theta, so it's f theta cosine theta, and then y you can write again as f theta sine theta. That's what you get. And then you can use the same idea to find the slope of for polar coordinates. So let's do that. Okay, so slope of the tangent line. So let's do that now. So let's say slope of the tangent line. So the slope of the tangent using an earlier argument, so dy over dx. And now the parameter is theta, so we write this one as dy over d theta divided by dx over d theta. So that means we need to take the derivative of y with respect to theta. So what we can do, we can replace y by r sine theta, that we know, and then divided by the same thing, d over d theta r cosine theta. Now we use the product rule. Okay, use the product rule. If you use the product rule, what happen? Take the derivative of the first one, multiply by the second one, plus take the derivative of the second one, multiply the first one. So r cosine theta. Same thing here, take the derivative of the first one, multiply by the other function, and then we have r, derivative of the cosine negative sign, so the negative r sine theta. So that's the formula you get. Okay, and then we know r as a function, so you plug in there and simplify. So that means as a formula you're going to get dy over dx equal dr over d theta sine theta plus r, which is given, cosine theta divided by dr over d theta cosine theta minus r sine theta. So let's try this as a formula. So that's a formula. So r is given, so r is given as a function, and it will be clear like when we do two examples. So now what we can do is there are a special case. So what's going to happen at the tangent line? Okay, tangent line at the pole. At the pole. Pole means the beginning. R equal 0 case. Okay, you stay at the origin. So that means just plug in r equals 0 here. If you plug in r equals 0, what will happen? You can see you can simplify this very well. So dy over dx is simply going to be if you plug in r equals 0, so you get dr over d theta sine theta plus 0 divided by dr over d theta cosine theta minus 0, and then you can see this simplifies and you get sine over cosine, sine theta over cosine theta, which is simply tan theta. Okay, so if dr over d theta not equal to 0, so that means we have this formula. So what happened? Dy over dx equal simply tan theta at the pole. Okay, this only works for the pole. So at the pole. Good. So those are the that's the only formula that we have. So let's choose to maybe just one example to see how it works. So this is the last example of this discussion. So let's do find the slope. Okay, find the slope of the tangent line. Find the slope of the tangent to the curve to the cardioid. There's a one curve called cardioid because it's shaped like a heart. Cardioid. R equal 1 plus sine theta. So cardioid has a special format. You see the 1 plus or minus sine theta has the shape of a cardioid, or 1 plus or minus cosine theta has the shape of a cardioid. So you learn these things in Calc 2 classes. When let's say theta equal pi over 3. It's a number that simplifies very well. So we like pi over 3 here. Okay. So how to do the problem? We know that r equal 1 plus sine theta. So that's the equation, and you can see the r is a function of theta now. So the slope is simply dy over dx equal dr over d theta sine theta plus r cosine theta divided by dr over d theta cosine theta minus r sine theta. So let's plug in there. So since this is like lengthy, I'm going to start in this line. dr over d theta, state the derivative with respect to theta of r function. You can see that means 1 plus sine theta. So once we do the derivative, it's going to be cosine theta. And we already have sine theta here. Plus r is 1 plus sine theta. And we have cosine theta here. Whole thing divided by dr over d theta again, cosine theta. And we already have a cosine theta here. Minus r means 1 plus sine theta. This is sine theta. And then you can see you can in the first one you can take cosine theta out as a factor. So if you do that, you get cosine theta, you're going to get 1 plus 2 sine theta divided by, in the bottom one you can see you have cosine squared theta Okay, let's write that. You're gonna get cosine square theta, and you also get minus sine square theta, and then minus sine theta. So you have minus sine theta, and using the double angle formula, you can write this one as cosine theta 1 plus 2 sine theta. We know that the cosine square theta minus sine square theta equal cosine 2 theta minus sine theta. So this is simpler than the original one. And you can see you cannot simplify this further. So you have to leave it like that. Now what we can do, we can evaluate this at theta equal pi over 3. So you can see when theta equals pi over 3, you have dy over dx, the slope, at theta equal pi over 3 equals to, just plug in, cosine pi over 3, 1 plus 2 sine pi over 3, and then we have cosine 2 times pi over 3 minus sine pi over 3. If you plug in the values, this is 1/2, 1 plus 2 times square root 3 over 2. Here we have cosine 2 times pi over 3, which is negative 1/2. Okay, so look at my trigonometry video. In that I explain how to simply find a value of any trigonometric functions. That's very, very easy. Okay, that's an easy way to do it using the ASTC and the reference angle. So you can simply say that it's negative 1/2 because in the second quadrant our reference second quadrant, so it is negative with the cosine, and the reference angle is pi over 3, which is 1/2, so it's negative 1/2. Okay, minus square root 3 over 2. So if you multiply the top and bottom by 2, you multiply the top and bottom by 2, and you can see that you're going to get a factor 1 plus square root 3 that get cancelled, so you simply end up getting negative 1. So the slope is negative 1. Okay, so that's it. The simplify is very well actually. So slope is simply negative 1. So if you need more steps, we can do that. So you can see what you get in the top is when after you multiply by 2, you get 1 plus square root 3 in the top. In the bottom, you get negative 1 plus square root 3. Okay, you can see that get cancelled, and you end up getting negative 1. Okay, that's what happened. Okay, so I'm going to give you an exercise. Try this problem. So find the slope. Find the slope of the tangent line. Find the slope of the tangent. Find the slope of tangent to the ellipse. You know that the ellipse is given by in this form, equation like that. Okay, so let's say 2 minus sine theta. So this is a ellipse. This we discussed in Calc 2. At theta equal pi over 6. Okay, so if you look at the complete video as a courtesy, see whether you can find the solution of this one and write it in the comment section. Okay, so good. Now that you know how to find derivatives of pretty much all type of functions, including power functions, trigonometric functions, inverse trigonometric functions, hyperbolic functions, exponential functions, and logarithmic functions, and you also know the implicit differentiation. So I'm going to give you some practice problems for you to try, and you can see the solutions for those problems in the description. Okay, but I will wait until at least one of you ask me to post those solutions. So if at least one of you ask me to post the solutions, I'm going to put the solutions in the description. Okay, so I will wait until you're going to do that. So these are the problems. So I'm going to call these practice problems. So practice problems. So let's see. So we're going to divide these into 4 problems because the 4 type of problems. So the first one I will just ask find the derivative of the following function. So find the derivative find the derivatives. So I'm going to say a y equal 3x to the 5th minus 6 over square root x plus 4 sine 3x plus e to the minus 2x. B y equal x to the 4th e to the negative 3x. C y equal, I'm going to call all the functions y, so it doesn't really matter changing. So 1 minus x to the cube 2x plus 3. D y equal x to the 4th plus 3 divided by 2x squared minus 1. And E y equal 2e negative 3t plus natural log 1 minus t. And then F y equal x to the 4th minus 3x squared to the power 5, the 5th power. And then G y equal cosine t to the 6th. We don't need the bracket here, it's clear. H y equal 5t to the 4 minus 8t plus 5 square root. And then we have I y equal e to the sine theta squared. And then J y equal e to the tan theta square root. And then K y equal base 3 t squared minus 1. L y equal tan sine x to the cube. And then M. So let's do a little complicated one. So how about sine cube cosine tan x squared. And then N y equal 1 minus sine theta 1 plus sine theta square root. And then we have we can skip O because that can be complicated. So let's say P. We can have y equal natural log x3 minus x to the 4th root. Okay, something like that. And then Q y equal, let's say, x to the cube, x to the fourth minus x, the cube root. That's, let me take a little more space so it's not clear. So let's change the problem. Yeah, so let's say x to the fourth minus x, the cube root, divided by x squared plus 5. And the r, y equal x square root x. And then we have s, y equal 1 plus x to the 1 minus x. That's kind of interesting. Then we can have t, y equal sine inverse 3x minus 1. And then we have u, y equal tan inverse, or the arctan sine x. And then v, y equal hyperbolic secant 3 theta plus 4 w, let's say y equal hyperbolic cosine secant theta. This simplifies very well. You can see it simplifies very well. So x, y equal, so this is also like really nice one. This simplifies very well. X sine inverse x plus 1 minus x squared square root. I'm going to star here because these two like simplifies very nicely. And then we have y. So let's a similar one but using hyperbolic sine function. So x sin inverse x over 3 minus 9 plus x squared square root. Okay, that's question number 1. And then in the other question, we're going to go with the implicit differentiation problems, parametric curves, and polar coordinates. Okay, so let's do that next. So the next question I'm going to call question number 2. Find y prime if, we can say if, the first question is x3 minus 2x y squared equals sine y. That's the first one. And the second one, 3x plus e to the xy equal y. And question number 3, find y prime and y double prime if x equal t cube and y equal 2t squared minus 1. And number 4, let's say find the slope. Find the slope of the tangent to the hyperbola r equal 3 divided by 2 minus 6 cosine theta. We know that this is a hyperbola using the polar coordinate. Okay, at let's say theta equal pi over 3. Okay, so try to do these questions and compare the answers in the description. And also I'm going to wait until at least one of you ask me to post the solutions, so then it's gonna be there. Okay, so thank you so much for watching the video.